Good morning. Good morning, everybody, and welcome to the second day of Learning for Dynamics and Control L4DC 2020. Thank you for joining. It's great to see everybody online. And before we start, we'd like to start with a few technical details, and we have some opening remarks.
Good morning.
Good morning. Just a few technical details. Good morning, everybody, and welcome to the second day of Learning for Dynamics and Control L4DC 2020. Thank you for joining. It's great to see everybody online. And before we start, okay, thank you. Let me go through these few technical details. We'd like to remind all of you that to engage with the conference, there are a couple of different ways that you can do this. So you can go to our website, l4dc.org, and you can click on YouTube live streaming. And if you do that and you log into YouTube or through your Google account, then you can ask questions of the speaker in real time. For each talk, we have a moderator who's collecting up questions. And some of the questions we'll be able to ask the speaker in real time after the end of the speaker's talk. And other questions we can bring over to the open review discussion, which you can also access through the website. And there you can go and chat with the authors of the papers and the corresponding posters. Let me say a few opening remarks. We'd like to thank all of our invited speakers and contributors. We'd like to thank our sponsors, Bosch, Merle, MathWorks, and TRI. And we'd like to thank ONR and NSF for their continued support in launching this conference. So with L4DC, our goal has been to create a forum that brings together pioneers and state-of-the-art research in the areas of control systems, optimization, machine learning, and related disciplines in order to create a prestigious annual conference that defines the state-of-the-art in learning for dynamics and control systems. And we feel that such a conference can have a tremendous impact, not only scientifically by bridging these areas, but also from a community perspective that nurtures a growing number of junior researchers working on this emerging interface. And it also provides a natural home for professional development for students and faculty. So following the success of the inaugural L4DC workshop, which was held last year at MIT, this is the second annual conference on learning for dynamics and control. In the long term, we'd like to sustain this event as an annual conference where the best results on this emerging interface are presented. And we aim to create a new community of people that think rigorously across the disciplines, ask novel fundamental questions, and develop the foundations of this new scientific area. So this year, and I'd just like to page through some of the folks who really helped us out with this conference. We formed a program committee consisting of 57 participants from L4DC 2019. We invited submissions of short papers addressing the topics that we discussed. We received 135 submissions, and then members of the PC were able to recruit reviewers for the conference. So we'd also like to thank the PC and all the reviewers. From this, a set of 14 papers are going to be presented or have been presented over yesterday and will be presented today as oral presentations. And then an additional 85 are being presented as posters on open review. Finally, we'd like to acknowledge all of you for your flexibility in the delay of our conference by one day, in order to acknowledge the need to transition to a real commitment to removing anti-Black racism in academic institutions and in STEM specifically. With that, so we're just paging through our multitude of reviewers. Thank you for all your hard work on this conference. Actually, a few of you see your name appearing twice. That means you reviewed more than one paper. Finally, on this last slide, we'd like to thank our organizing committee and our website designer, Marius, and also our moderators who have been helping us gather the questions on YouTube and asking those of the speaker. Okay, so with that, we'd like to transition to our first invited speaker of the day, who is Leslie Pack Kaelbling from MIT. And let me give a brief introduction to Leslie. And the moderator for Leslie's talk will be Andrea Baichi, who's also online. Okay, so Leslie is the Panasonic Professor of Computer Science and Engineering at MIT. She's in the Department of EECS. She's a member of the CSAI lab at MIT. And she's the founder and editor-in-chief of the Journal of Machine Learning Research. She's also a fellow of the AAAI, which is the Association for Advancement of AI. Prior to joining MIT, she was a professor at Brown, and she also held positions in the AI Center at SRI and Telios Research. Leslie is an expert in AI and its application to some different areas. So designing situated agents, really understanding the nature of intelligent behavior in the physical world, and trying to understand that for development in robotics. She works on mobile and manipulative robotics and develops methods to allow them to operate robustly and flexibly in complicated, uncertain environments. She works in reinforcement learning and decision theoretic planning. So it's a pleasure to welcome Leslie today.
Okay, thank you very much for the invitation to speak here. This is a great conference and a great opportunity. And I am looking forward, I'm sorry not to have the audience here in front of me, and I am looking forward to questions and comments, and I hope that we can have a robust conversation at the end. So I started out with this kind of high level and slightly pompous sounding title, doing for our robots what nature did is going to ship out robots that are going to operate in the outside world. And my job as a software engineer, so I'm assuming that the hardware is not my problem, the software is my problem. My job as a software engineer is to figure out the policy, the program that's going to go inside my robots. And the way I think about a policy is it's something that's going to map the history of observations that the robot has gotten and actions it's taken into the next action. Okay, so that's what I take to be my job. So how do I think about what the right program is to put in the head of the robot? So what we have to do then is to think about you, the customer. You come to me and say, I need a robot or I need several robots, and here's what I can tell you about the domain that the robot is going to be in. And maybe I don't know exactly the domain, maybe I know a distribution of domains. So it could be that the distribution is very narrow, that you're hiring me to make robots that just work in your factory to do something very specific. Or it could be that the domain is very, very broad. You want to make a household robot that could work at anybody's house. But whatever it is, you have to tell me, the factory, the distribution of domains that this robot is going to have to operate in. And then I have to come up with a program that's going to work best in expectation over that distribution of domains that the robot might find itself in. And I've written it kind of specifically here in terms of an additive reward. You could formulate this a little bit more generally, but this is the basic idea, the way that I think about the problem that we need to solve. And I'm actually pretty happy about this framing of the problem. One of the reasons that I'm so happy about it is that if we can write down an objective function like this, then there is some optimal policy that I can put in my robots and send them out into the world, and they'll work as best they can in the domains that they find themselves in. And we don't have to argue about whether it should or shouldn't do learning and whether it should have symbols or neural networks or control, whatever. We don't have to argue about that. We just have to find the best program according to this metric. Okay, so I'm happy for a brief moment. And then I become sad because I say, well, okay, maybe I've made the specification easy, but I've made my job very difficult, because now I, as a robot engineer, after you come and tell me your distribution over problems, I have to come up with this policy. And that's hard. And that's what I really want to spend time talking about today. So one of the things we can do is to think about the character of that distribution over possible domains the robot's supposed to work in. So one dimension of variability might be like, really, how complicated, how rich is the variability of the domains and problems that the robot has to work in? And that, generally speaking, that kind of richness also induces a kind of complexity of the policy that we need. And another dimension that's really important is, how much uncertainty do I in the factory have about the actual world that the robot will encounter? So I want to use these two axes. How complicated, how variable is the set of problems the robot will have to face? And how much do we know about it in advance? And according to these axes, then there are kind of different points, which I'll discuss in a fair amount of detail as we go. Okay, so now we're going to think about a couple of questions. First of all, we want to just kind of frame the question of, well, how could we find a good policy? So you come and you tell me a distribution over the problems. How do I come up with a good policy? The way I want to think about it is to say, well, okay, we have to pick some kind of class of models and some way of acquiring those models. This is what we, the engineers, have to do. And we want it to perform well. And we also, in some way, want to minimize the construction cost, how hard we have to work in the factory to make this robot program. So to think about the construction cost, I think we have to take two kinds of costs into account. There's the cost that the engineers pay. There's specifying models, making simulators, labeling data, whatever you have to do. So that's work. And then there's work that the machines have to do in the factory, running optimization problems, parameter tuning, and so on. And really, when we think about this problem, our problem as engineers is that we should pick a model class where humans have insight so that they can really kind of make the process efficient and effective, where the optimization is easy, and where learning methods that we use will generalize well. So that's maybe a way to think about our objective function now in the engineering problem. And so how can we think about picking a model class? Well, there's a lot of research about this, and I just want to kind of illustrate a whole family of model classes, right? Our favorite model class is that we could represent a policy just by writing down a policy. So that's pretty easy. It turns out that policies are often hard to write down, right? Lego, when you're programming a Lego Mindstorms robot, you say go forward, turn left, and so on. So that's a way to write a policy. Or we could try to find a policy using policy search. But we find that that's not so good for humans or really for learning algorithms, in the sense that as the horizon gets long, it's hard to find policies. So often instead, we frame the problem in terms of finding some kind of value function. Then we can do some kind of gradient optimization online relative to the value function. So that's a move we make. It's still a way of representing a policy. It's just slightly indirect. And sometimes we find it's easier to learn the value function. But value functions are not the answer to all the problems. And in particular, I always like to call people's attention to the fact that usually value functions are useful to have when the dynamic programming property holds, when we're going to be revisiting states often enough so that it's worth finding the value function over the whole space, that will pay off later. But in situations where we might only visit a small subset of the states, that might not be very efficient. So what else could we do? Well, we could say my representation for a policy is going to be something more like a model predictive control setup, where we say I have some kind of a planner, and that planner takes transition and reward models, and maybe it takes a policy or an approximate value function to help with search guidance, and it's going to make plans online, but still it satisfies the spec of a policy. It takes observations and gives out actions. I'll talk a little bit later about how this might be good, but it could be that doing that in a very raw space is not okay. We might want to interpose some more complicated modules, maybe something that abstracts the observations into a representation of an underlying state, maybe some lower level control loops so that the planner doesn't have to operate at the lowest level. And we might even want to add some additional hierarchical abstraction into this. So there's a whole family of of representations of policies, and we should think based on our domain about what one is going to be most appropriate. So that's a family of representations of policies. Let's think about ways that we have of obtaining policies. So the easiest, most classic thing is just engineering, and engineering is awesome. Engineering makes this Atlas robot do parkour. Right? So there's, we know roughly what problem we want to solve, and we kind of reasonably directly write controllers for that problem. This is a problem where there's a specific thing that this robot is supposed to do, and we, the engineers, know in advance what it is. But here's another example of a problem that I would argue is in the same class, right? So there's this amazing example of a robot learning to manipulate a Rubik's Cube. And what's interesting about that is that it's a fairly narrow problem, and it's known in advance, really, that problem. But yet we use reinforcement learning to address it, right? At least some of the time. So what does that mean? When we know everything about a problem, why are we using a learning method? So I have a little digression here because I want to talk about the use of reinforcement learning inside the factory, which is in fact, I think, where it mostly gets used lately, right? So we could say, all right, here I am in the factory. I'm supposed to make robots that go out in the world. And what I'm going to do is actually, since I know the problem that I'm supposed to be solving, I can build a simulation for that problem, connect up a reinforcement learning algorithm, and run that as a kind of a compiler. And that gives me out a policy and now, or a value function now, and I can execute that in the world. So this form of reinforcement learning, to me, it's like a compiler. It takes in a description of the world, in this case, in the form of a simulator, and it gives us out a policy, which we can then put out in the world and run. There's some important things about this setting of reinforcement learning. One is during the learning process, reward doesn't make any difference. Right? So the classic exploration exploitation trade-off doesn't really apply, because while we're learning in simulation, we could beat our head against the wall as much as we want, and it doesn't really matter. It doesn't really matter how many times we interact with the simulator. Fundamentally, I think the measure of merit for this kind of a setup and this kind of a problem is, as a function of how much computation time we spend in the factory, how good is the policy that we get? So we're turning a simulator into a policy. Then we'll take that policy and run it in the world. Okay, so that's a way to get a policy. Then we can add more structure to the policy. So one thing that you might do if you look at AlphaZero and MuZero is that now their policy is described in terms of a search mechanism and a policy. And what I want to do now is talk a little bit about a case that goes all the way over here to the right that can solve quite complicated and general problems using a fairly complicated policy representation. And what I want to do just briefly is highlight some interesting differences between approaches that might do RL in the factory versus approaches that might do planning online. So they address, in some sense, a similar class of problems. Okay, so RL in the factory versus planning in the wild. The question is, what are the engineering trade-offs that we need to make, right? So in both cases, there's an engineer, in both cases, they're trying to make a policy for the robot, and they need to build in the reward or the goal. So how does a person who's making a reinforcement learning, using the reinforcement learning offline strategy, code in the reward? So one thing that we did is we looked at this meta world suite of problems that was made as reinforcement learning problems, but there are also examples of problems that are pretty classically solved by planning methods in robotics. And so we wanted to kind of just think about this whole class of problems. One of the things that's interesting about that problem class is to use reinforcement learning to solve those problems. It actually requires a fairly detailed and specialized reward function so that the robot can get guided to the goal often enough so that it can learn a good value function. So it's a non-trivial task to specify the reward function so that it's smooth enough and local enough that the local exploration methods can reach the goal often enough so that the thing can learn the value function it wants to learn. On the other hand, for planning approaches, you can write the goal down pretty much directly, right? So when we apply a planner to these problems, we say, well, our goal is that the pose of the target object should be somewhere. And the planner figures out what to do. Okay, so what else do we have to specify? In both cases, we have to specify, in order to make the simulator, we have to say, what are the kinematics of the robot? Where are the objects in the world? We have to explain that same stuff to the planner. The RL method still needs to build the simulator, so it needs the physics of a simulator, although that's a very general purpose thing and easy to acquire these days. The planning, the person who's trying to use planning online to solve this problem has to specify a lot more stuff. And that more stuff, the question is, how much more is it and how hard is it to specify? And so what I really want to spend time now on is thinking about ways in which we can describe difficult robot manipulation problems so that a human can write those descriptions down and the thing can operate fairly effectively. So the question is, if we're going to do online planning, how should we formulate that problem? And the most straightforward way might be to say, I'm going to think about using the simulator as my domain for planning. I could think about the action space as being low-level joint commands. I have a long horizon. I don't necessarily have a heuristic unless I learn it. But if I learn the heuristic, then I have to be able to get to the goal in the first place. And if I don't have a value function, a reward function that's local and tells me how to get to the goal, then I can't really solve this problem. Instead, we tried to build models at a higher level of abstraction. And in particular, we would like our action models to be lifted. That is to say, to be articulated independent of particular objects, so that I might be able to describe the action of picking up a pencil in a way that's generic. It's not about this particular pencil. It might not even be about pencils. It might be about objects or cylinders. And I want to be able to describe my model compositionally so that I can say something about picking up pencils, something about moving my hand, something about throwing things. And I can take those pieces and parts and put them together in combinatorially new and rich ways to describe very complicated sets of actions. So I would like to construct a model that's like that and that makes the planning easier. So it's going to be something that lets us do hierarchical planning, which makes any given horizon short, which makes the individual planning problems easier. And one thing about a certain class of abstract models is that they sometimes give us leverage in coming up with a heuristic. So that can be very useful. So I want to talk briefly about a model for an abstract model for motion planning that I think is very helpful. And it's known to a certain segment of robot manipulation people, but not too broadly outside of that. And the abstraction is something called multimodal motion planning. So for right now, we'll assume that the robot and objects are rigid objects. They're kinematic chains, so the objects can be jointed, and we can represent the state of the world in terms of poses and shapes of objects. We'll introduce the notion of a mode. So if we have a very complicated space, we have a robot with many joints and also hundreds, let's say, of objects in a room. Maybe I want to find a particular object in my kitchen. We can't think about controlling that whole space at once. It's very high dimensional and it's very underactuated. I can't sit here and imagine moving an object in the other room. Although I can move that object, but I have to do that by moving myself over there. So we can think of a mode as you can think of it as a small set of state variables that you have sort of a smooth dynamics over at the moment. So a mode that's easy to think about is a robot moving in free space, right? So I can control my joints and that's all. Or you might say, holding this pencil in this grasp, that's a mode. I can move, and now I'm controlling my joints, and I'm also controlling the pose of the pencil under some constraints about the relation between me and the pencil. So this notion of a mode, I can say, it allows me to change some state variables while all the other ones remain fixed. There's a notion of a mode family, which lets us abstract a little bit. So a mode family might be that I am grasping the pencil, and what picks the particular mode would be my continuous relationship to the pencil. And you can specify a mode family generally by which state variables it changes, and by a set of controllers that let you enter the mode, move through it, and exit to another mode, and some tests that tell you whether you're in these mode intersections. So this picture, I love this picture. It's not from, so the basic ideas here came from Chris Hauser, but this recent paper from Kingston and so on illustrate the space that you have in a multimodal motion planning problem. So imagine that we live in this very high dimensional space, which is the configuration of the robot and the poses of all the objects. The robot, when it's moving in free space, you could think of it as corresponding to that green submanifold. It can only change a few state variables at the moment. It can move smoothly in that space. Now, when I pick up the pencil, maybe I enter that pink manifold, right? So I'm in the intersection, and now I can move around in a different subspace, which is a subspace where I'm controlling my variables and the pencil's variables. And there are the underlying structure of the space is a thing called foliation. And so the topology is really interesting, and you can reason about how you move among these manifolds and within them. And that gives you a very powerful abstraction for robot planning. So we took the meta world and thought of that class of problems and tried to frame it as a multimodal motion planning problem, actually a lifted one. So abstracted away from objects, we defined some mode families. So one mode family is free space motion. Another one is moving while holding an object. So when I pick, I move into one of those modes, and then when I place, I move out of it again. There's a mode that's about pushing objects. There's a mode that's about operating some kinematic objects. In this world, there are some handles that you can turn and doors you can open. And so these mode families are quite general, right? We had to define 4 mode families. They're lifted in the sense that they apply to particular objects. And once you apply, you talk about pushing this particular object, then to really nail the mode down, you have to say, I'm going to push it with some certain set of contexts. Using those things though, and putting them into our planner, we were able to kind of immediately solve these problems in a quite general way. So here's a set of them, and here's a bunch more of them. We're using a different robot just because we did it very quickly. And what do we do? So there were 50 problems. We solved 43 of them so far. We would need another mode. There's some cases where the robot kind of moves things by rubbing up against them. And that's another mode. There's some insertions that are very tight that work in MuJoCo, but I'm not sure that they would work in the world. And so there's something there. Anyway, this all doesn't involve learning. Okay, so I've been talking and talking, and I haven't really talked that much about learning, and I have to actually finish pretty quickly. What we have done, I'm actually gonna skip this movie, although it's a cool movie, and talk about how does learning come into all this? So how does learning come in? Well, when we have uncertainty about the domain that we're operating in, then we have to actually, the robot in the world has to do learning, right? So we have to do learning in the wild. The original reinforcement learning formulation was about learning in the wild. And so this is a kind of caricature. Imagine I asked the robot for coffee and it's doing reinforcement learning in my kitchen. That makes me not so happy. So now, when you're doing learning in the wild, you have to really take seriously that some of the actions that you take in the wild will cause damage, and all the rewards count now against you when you're learning in the wild. So that you have to be careful about that. You can use meta learning to kind of interpolate between the classical thing and the RL where you don't know anything at all. What I want to do is just end by talking about an architecture where we hope to take this kind of hierarchical planning model that we've been using to do a bunch of things and think about how we can learn all the models, right? So we have designed an architecture and we've built the models. Now we want to take the models out and learn them instead. So we'll use one of these policy architectures that I talked about early on that has a bunch of different pieces and parts that parameterize the way it behaves. And what we've been doing in our research group is learning the models. So we can learn models that describe operations at a high level, new modes, basically. So you might imagine that pouring a liquid is a mode, and we can learn about that mode, how you enter it and execute it, and how you move through it. We use some Gaussian process methods to do that. We care a lot about sample complexity. So here we had to do some learning, and it involved picking up a lot of chickpeas. So we wanted that to be efficient. But what we can do is take a robot that already knows how to do pick and place, learn some new operations reasonably efficiently, and then just add them right in, because we have a planner that understands how to assemble different skills that involve moving through different modes. So here we can pretty generally put objects on the table, the robot there moved the green object out of the way of the blue cup, just because it understood about occlusion, not because it has a policy for that. There's an example, I think it's the one after this, where the robot actually pushes the bowl into the workspace in front of it, so that when it picks up the cup to pour from, the bowl is in a good space, right? So again, this wasn't coded in, and it wasn't learned either. It was done by inference because it understood what was necessary in order to do pouring. We've also been doing some learning where we try to take let's see, actions that get derived by planning and compile them into policies at a high level of abstraction. We've been learning search control at a high level of abstraction, where we really want aggression, sort of aggressive generalization, so that, for instance, learning from how to move boxes around in this apartment building, we can learn how to move objects that are in the cupboard. And we can do Q learning at a high level of abstraction that we think will do better generalization. So all of these things put together, we hope will give us a general kind of bootstrapping approach that would let a robot do continual learning in the wild, right? It would start out doing some learning in the factory, and then it would come to your house and do a little bit more learning in a compositional way. You could imagine a loop which might go like this. You pick a target property. The robot might say, I really wish that I could get some beads in this cup, something like that. Try to plan given your current model. If you could make a plan, try to execute it. If you execute it and it doesn't work, you'll learn something about the dynamics that will help you fix your model so you'll behave better next time. If you can't make a plan, then figure out why not. Maybe you need a new skill. Maybe you don't know how to take the top off the jar, which is what you really needed. Or maybe you have to formulate your models in a different way that would admit a plan. When we get data, we can update our predictive models. We can define new concepts to help us compress our descriptions of how the world works, and then use those as targets for learning policies to try to achieve them. We can reify new latent properties. If I find that there are some objects that I just can't pick up, maybe eventually I figure out that there's a notion that they might be stuck to the table. So what we hope is that we can loop and learn and build and ever increase a kind of a level of abstraction, so that we can make a robot that could come to your house and you could teach it new things without too much time and trouble. So the work that we're doing builds on the work of a lot of students and colleagues. And with that, I will say thank you. And normally I would let you watch this video of the robot making mistakes, just so that you know we really did this while I took questions. So thank you for your attention, and I look forward to answering the questions that appear on YouTube.
Thank you very much, Leslie, for a really interesting talk about this combination of multimodal motion planning with model-based and learning and continual learning. I'm going to pass it over to Andrea, who's been tracking the YouTube questions and can ask you some of those.
Yeah, thank you so much, Leslie. That was a fantastic talk. I have a few questions of my own. I know that Claire has some questions that were posted on YouTube, so let's just get into it. So the first question that I actually had was, in the multimodal motion planning, do you assume you can estimate really well which mode you're currently in, or is the estimate of which mode you're in somehow incorporated into the planning process?
So that's a good question. In the standard multimodal motion planning framework, the view is that it's completely the world is completely observable, and that in fact multimodal motion planning is just the planner, so it doesn't worry about the loop being closed at all. So you can think that's the kind of the model predictive part of the model. In real life, of course, when we do things, this particular robot that I was showing you it just re-estimates, it uses its perception, and basically every time it takes a primitive action, it tries to re-estimate what's going on, and it just replans all the time. In another version, we actually do belief state estimation. We keep a distribution over what's going on. And in fact, we do the motion planning in that, the multimodal planning in that case, actually in belief space. So it reasons explicitly about information gathering. This particular case doesn't.
Cool. Claire asked if you could comment a little bit more on the computational challenges of planning through these mode switches.
Right. So that's a really interesting question. So the mode switches are super tricky because they're even lower dimensional than the modes, right? To grasp something, I have to get my fingers like near an object and ready to get it. So we use samplers, sort of generative models. You have to have, the key to making one of these things work is that you need samplers that give you configurations that are in the mode intersection. And classically, those are implemented by humans. You can make them sometimes by optimization, by kind of trying to sample things that are not in the intersection and then do some local projection into the intersection. We're also doing work though on trying to learn samplers, so learn generative models for, that would be like learn a generative model for good grasps of my hand, good relations between my hand and the object. So yeah.
There's a recent question from YouTube that was posted. The question is, can I understand MMP as a sort of sample-based approach to hybrid system planning?
Yes, that's right. In fact, well, multimodal motion planning is a problem class, not an algorithm. So at that level, it's a class of problems. But there are many of the solutions for multimodal motion planning problems are sample-based. But you can't, you know, you would like to say, oh, I would just like to take RRT and somehow apply it in this high dimensional space. That doesn't work because the high dimensional space has all this weird low dimensional internal substructure. So you have to manage, the way people typically think about it is that there's a discrete choice of the mode families that you're going to move through, then a continuous choice of the parameters like the grasps and the placements that pick the modes, and then some RRT-like planning to move within the modes.
Thank you very much, Leslie. That was a fantastic talk. And we really appreciate your giving a talk in this new online format.
Excellent. Thanks so much.
Now, Leslie, could you, oh, great. Thank you for stopping to share. And John, I think you can now share your slides. So as John starts to share his slides, I'd also like to introduce David Fridovich-Kyle, who is going to be the moderator for John's talk and will be collecting and tracking the questions on YouTube. And I'd like to introduce John. Okay, so John Lygeros is a professor for computation and control, and he's the head of the automatic control laboratory at ETH Zurich. John is a fellow of the IEEE. He's a member of the Institution of Engineering and Technology and a member of the Technical Chamber of Greece. He's on the IEEE Board of Governors. He's on the Scientific Steering Committee of the Newton Institute and is on the Board of Governors of IFAC. Before joining ETH Zurich, John held previous positions at the University of Cambridge and the University of Patras in Greece. John is a pioneer in modeling and analysis and control of hierarchical hybrid systems. And he's done fundamental work in optimal control and its interface and connections with reinforcement learning. He works in problems in large-scale systems such as power networks, surveillance systems, and air traffic management. And he also works in problems in biochemical networks. So it's a pleasure, John, to have you talk today, and thank you very much.
Thank you, Claire. I hope you can hear me.
Yes, we can hear you.
Great. Okay, so yeah, thank you very much. Thank you for the introduction, and thank you for inviting me to give this talk. It's a great pleasure to be here. Today, my talk today will be about optimal control in a sense, but using data. And this is work we've been doing in our lab, several guises. I'll just touch upon a couple of them during the talk. So the idea is to do optimal control, and if I can get my mouse to work, yes. And basically, I'll start by a brief overview on what's model-based optimal control, the standard way of doing optimal control in the literature. which is you have a system that you want to control. For the sake of the argument, I just wrote just a vanilla flavor linear system in there. You collect some data from the system offline, and you use this data to build a model. So you go through some system identification process, and you generate a model on the right here. If you know the model, the system is linear, you generate a linear model where the matrices here, A hat, B hat, C hat, are sort of supposed to be related to the matrices that you started with. Hopefully will be related to the matrices you started with. Then you go offline, you do all of this. Online, you get more data. Time K, you get a new measurement. So you have a bunch of points that you measured recently from your system. And then you use this to form an estimate of the state of the system. You go through some Kalman filtering or state estimation procedure. You use that information to compute an optimal control, a policy, or a model predictive control, some control inputs that you then apply to the system. Okay. So you see in this picture, there's data all over the place. There's data up there. Wherever you see data, you need to do some kind of regularization. That's happened in system identification, solving a least squares problem or putting some prior or something like this. And you have data online as well. You have to do more regularization there. And there you use the model itself. Usually, if you do a Kalman filter, you assume the model is linear, and you use that to regularize the data you measured online. Okay. The model is used a couple of places. The model usually also used to compute the optimal control, of course. Okay. So what we've been thinking about for a few years now is, can you do this? It seems like a bit of a shame. You have data all over the place, and then you have a regularization all over the place. Would it be possible to just get rid of this part and do everything directly from the data? So save yourself all this multiple levels of regularization and so on and so forth, and go and do everything directly from the data. When doing the talk, I realized I put a little bit too much color coding in. I will use this red blobs, dotted red blob for offline data and solid red blob for online data. So I'll try to be consistent with this, and hopefully that's not too complex of a protocol to follow. But in any case, if you get rid of this, you look in a situation like this. You have your offline data on the right, have your top right, bottom left, your online data. All of it goes together in some policy computation. You do the regularization, and then you shoot that off to the system, the result to the system. There's a couple of ways you can go about doing this. One is database dynamic programming, for example, where you try to estimate, actually Leslie mentioned this as well, value functions or Q functions from the data. We've done quite a bit of research on this in recent years using linear programming formulation, where you, instead of looking at Bellman operators and fixed points of Bellman operators, you look at a linear program that's equivalent. You solve a linear program that's equivalent to get your value function, your Q function, depending on what you're doing. This is very nice, theoretically very elegant, very powerful, has been around for maybe 30 years. But practically, when you try to do it for control system, it turns out you have to solve an infinite linear program with infinite number of decision variables and infinite number of constraints. So that's a very difficult thing to do usually. We try to do computational approaches for this, using getting approximation guarantees, seeing if we can do data-driven approximations, and so on and so forth. It's a very interesting topic. It actually touches upon Q-learning, reinforcement learning on the one side, also seminal work on approximate dynamic programming by, for example, Dimitri Bertsekas or Ripam Winkel in the control community. But this is a topic I actually talked about quite a bit in the last couple of years. I gave a talk in Berkeley, for example, and the European Control Conference about this. So many people have heard me talk about this, including all of the organizers. So today I thought I'll talk about something else. I'll talk about a very different approach on a very related problem. And this is what we call data-enabled predictive control. This is joint work with my colleague, Florian Dörfler. DeepC is the short name we invented for data-enabled predictive control. And the idea is to go back to behavior theory and something called the fundamental lemma and derive model predictive control formulations where you replace the equality constraints you have to find in MPC to encode the dynamics with subspace constraint based on data matrices. We've done several tricks for doing this. I'll tell you a little bit about those. We've also done some applications. This is a quad rotor flying with this method. At the moment, it's collecting data, a random perturbation on top of a stabilizing controller. Once it figures out what it's doing, it's going to use this data to do step responses in the flight. Now it's going to the left, it's going to go to the right in a moment. It's going to be moving around the space using just the data it collected and solving an online optimization problem using this data. This is Toy. This is in the lab. It was a master thesis of Ezat. His name is there in the bottom. But we've also done some more serious things on power systems and building control, which unfortunately I won't get into in detail today. Okay. So that's what I'm going to be talking about. This is quite a rapidly evolving field. It's already been around for about 20 years. The work of Willems, Rapisarda, Markovsky, Demur, where they sort of quantified the notion of persistence of excitation for this behavioral approach. And then Markovsky, Demur, and others continue to work on it over the years. Recently seen a lot more attention. A number of groups, you see some listed there, have picked up on this approach and are using the same type of approach to solve model predictive type control problems online, or other types, robust control, and so on and so forth. Okay, first of all, credit to the team. This is the people who did all the work on this. Jeremy Coulson and did much of the initial development on DeepSea, and together with Paul Bossat on the right, supervised ESAT on the, for example, the quadrotor study. Linbin did the work on the power systems, and Daniela the work on Kalman filter that I will talk about. Generously funded by the ERC, as you can see. And of course, last but not least, my dear colleague Florian Dörfler, whom you see here attending CDC 2017 in Melbourne. I imagine Melbourne must be somewhere in the background. Okay, so this is what I'll talk about today. I'll start with introducing MPC and how it connects with this DeepSea, and then talk about how to do regularization in this context and how to use, when you get additional data, how to make use of this additional data. So I'll follow through these blocks during my talk. So I'll start very simple, deterministic linear system, LTI system, the simplest thing you can think of. This is the dynamic equations. I'm going to be looking into a tracking problem for the sake of the argument, nothing special about tracking. I have a reference signal I would like to track, RK, and I want to track this signal as well as I can using the minimal control effort subject to input and state constraints. And typically, when you do model predictive control, you get these optimization problems where you have a cost for doing the tracking, a cost for the inputs, and constraints for the inputs and the outputs. If you have a model, you do MPC, right? In runtime, you collect some data. This is in the red box in the top. You get some data for what happened in the recent past. You formulate an optimization problem, solve the thing, apply the first input, and repeat the process. That's the principle of receding horizon control, okay? I realize this is a bit of an eyesore for most people, this optimization problem. Let me parse it very quickly. This is the same problem as in the previous page. It has a bunch of components. The two components are the specifications, the blue components there, the tracking and the input cost are the specification. I want to minimize that. And I have constraints on the inputs and the outputs, and I want to respect these constraints. So this is the specification I was given for the problem. And then the two sets of constraints in the middle are where the model is being used. It's being used for two purposes. First of all, you do state estimation. You have the red boxes is the data that you have available, and you want to estimate the model of the system. And you want to estimate the state of the system. And then once you've got the state of the system, you can use the same model to do prediction. And when you do prediction, you get these equations up there that allow you to predict the future, basically, using the model. I realize this is simplistic. I apologize to MPC experts about this, but it's just to get the main idea across. I know there's much better ways of doing state estimation and formulating optimization problems, so you can do smarter things than this simple thing. Okay. Okay. What if you don't have a model? If you have a model, you can solve this optimization. If you don't have a model, but you have access to data, this is the dotted red boxes, the data I have available offline. If you have access to this data, you can, for example, try to identify a model and then do MPC using the model. That's one way to do it. You can also do different things. You can, for example, take this data, chop it up in bits, and form Hankel matrices with it. So I take the data, remember I'm looking some steps into the past to estimate the state and some steps into the future to estimate the output. And then I form Hankel matrices with this data. These are block Hankel matrices. Basically, I take this long sequence of data, I put it in one on top of the other until I reach the desired horizon. So I shift by one as I go down, shift by one as I go to the right from the Hankel matrices. This is what you do also for system identification. That's the starting point for this type of block Hankel matrix. If you do system identification, you try to factor the Hankel matrix, or if you don't want to factor the Hankel matrix, you can do something different. You can use the Hankel matrix to generate more trajectories. You can take linear combinations of the columns of the Hankel matrix, and it turns out, that's relatively easy to see by superposition, you will get another trajectory for the system. It's a bit more interesting than this. In the Willem's paper that I mentioned earlier, there's actually a theorem, this is called the fundamental lemma, they call it the fundamental lemma, which is basically under some conditions of persistence of excitation, not only do you get other trajectories by taking linear combinations of the columns of the Hankel matrix, you get all trajectories by getting linear combinations of the Hankel matrix. Okay. Now, this is quite interesting because now it turns out, as you see here in the bottom, if you want to generate a new trajectory of the system, all you have to do is take the Hankel matrix you form with the historical data, multiply with some vector g, get something in the color span, that's a new trajectory. So that allows you to write an optimization problem, the same as the optimization problem before, only you have your online data, you put it there, you have your offline data, you put it there, the rest is exactly the same. And this optimization problem does what the optimization problem in model predictive control did before. The past data you use to estimate the state implicitly. There's no state there, but just fixes the degrees of freedom that are related to the state of the system, the initial state of the system. And then the rest you use to predict the future. The rest of the degrees of freedom are the degrees of freedom you have for predicting the future. This is a program, a mathematical program, a QP in this case, if depending on your constraints, that you can actually write using just the data with nothing else. You don't need any model. And perhaps not very surprising, you can prove that this actually does exactly the same as a model predictive controller. This is a fact from a paper that we wrote last year with Jeremy Coulson. It got the Best Student Paper Award at the ACC last year. And this is a simulation on a quadrotor model that actually Melanie Zeilinger uses in her class on model predictive control, which basically shows that the behavior of the MPC controller with perfect state estimation and of this deep C controller with this optimization problem based on data is identical. Okay. So that's if you have a perfect world. That's if you have an LTI system and you basically can use it to make perfect predictions. Okay. Now, the world is not perfect. The world is not perfect. For this reason, you need regularization. So how does the regularization come into the picture here? The world is not a deterministic LTI system. It has uncertainty. For the sake of the argument, I'm going to just denote this uncertainty like an additive thing that I put to my deterministic linear time invariant system. So it's this term here, VK, that I added there. Okay. Now, I'm not being very prescriptive here. What could this be? This is anything that is not a linear time invariant system. For example, if you're doing linearization, this will be your linearization error. So if your model is, your system is really nonlinear and you're linearized it, that's what's left. That's linearization. Or if you're doing stochastic system, that could be the stochastic noise that you put in there, right? So it could be a stochastic linear time invariant system, that would be the stochastic noise. Now, it's quite easy to see that in this setting, if you try to do what I just described, where you take historical data and you formulate constraints using that and try to solve a model predictive control problem with this, you immediately run into trouble. Why do you run into trouble? What if you have, for example, linearization errors? What will happen then? This is the optimization problem, the constraint that you put in the optimization problem, where you have the online data and the offline data. If your system is nonlinear, these two are incompatible now. You can no longer write the behaviors of the system as a linear combination of past data because the system is nonlinear. That only holds for linear systems. So you won't be able, your problem becomes automatically infeasible. You won't be able to find a linear combination of your past data that exactly matches the behavior that you have observed from the system online. So you get infeasibility. See, related problem, if you go to a stochastic system, there is probably the opposite problem. There, under very weak assumptions of what the noise on the system is, it's relatively easy to see that you will be able to reproduce pretty much anything because of outliers in the noise. So any future evolution of the system will be compatible with the data you have collected from the past. So your model is no longer predictive. You can predict pretty much anything, and you can't really use it for making valid predictions about the future. Now, what can you do in this case? Well, regularization. That's what you do when you have a lot of data and you sort of doesn't quite match your model. This is how you could put regularization here. These are two regularization terms I added to my optimization problem. I'll flip one back to point out the color coding. For the first problem here, the green problem where you get inconsistency in your past data, this is what you have, what the estimation is, the regularization term is here. You just relax the constraint to penalize the deviations from the past data. That's the lambda y here term that penalizes deviations. And for the problem where you could pretty much do anything with enough outliers in your noise, you penalize large values of g to make sure that you don't leave these degrees of freedom to the system. On purpose, I'm being a little bit vague on what kind of norm you put there and what kind of regularization. You can select different norms and you can tune these regularization parameters to get different effects. There's actually an interesting discussion, which I won't get into. This second regularization terms that relates to distributionally robust optimization, where you think of robustifying against instances of the noise that you have not seen in the historical data. You need to tune the regularization weight, so you need to do a little bit more work, but you can use this trick to get this method to work on nonlinear or noisy systems that you would not expect it to work. This is an example where we did this. This is work of Linming Huang, who was a visitor in our lab with Florian last year. And this is a power systems case study. This is a HVDC line inside a power system, an AC power system. There's there are low-level controllers controlling the substations that connect the HVDC line on the bottom and the top here. And what we're doing is we're trying to figure out the set points of these low-level PI controllers that control the DC line. You see the results on the plots here. You have okay, it's again color-coded. The orange thing here is if you have the system uncontrolled and you see sustained oscillations in the orange plot. At time 10, you switch on the controller. Sorry, the orange plot is the controller that we have implemented. The gray over here is the uncontrolled system. Sustained oscillations in the gray. You switch on the controller. The orange one actually very quickly eliminates these oscillations. This is 3 of the buses that are being measured. In blue is, okay, you could say, why don't you do system identification? You could do system identification and solve an MPC problem. If you do that, you get the blue curve here, which is not nearly as good as this sort of direct data-based model predictive control without the model, deep C problem. So you do get some benefit by applying these regularization terms, and you can get it to work in quite complicated high-dimensional systems using just relatively few observations. Okay, so that's basically what is the main idea. Throw away the constraints in a model predictive control problem and replace them by constraints using data. Throw away the model constraints. Now, what are we doing now? We basically trying to understand what it all means. I'd be lying if I said I knew the answer to this first question. We're very actively researching this. Stochastic behavioral systems is an open field. There's very few publications on this domain, and we're looking into what you can do there. Distribution robust or randomized optimization that I mentioned already, relations to system identification. I'll spend a couple of minutes, my last couple of minutes, talking about the second point: can you make this work? You can make it work, but you need to think a little bit about it. You need, for example, to tune regularization parameters. This is a plot from one of the papers where basically you get this a typical curve you get by playing around with the regularization parameters. You get a sweet spot. If you over-regularize or under-regularize, you get very poor performance, but then you get this optimal point. You have to figure out where this optimal point is. As you say, this is only relevant if we move away from the deterministic LTI system. The deterministic LTI system, this thing works perfectly, theoretically at least. The question I'm going to spend a couple of minutes on is what if you have more data? What if you have more data available offline? What if you have online data? How do you make best use of it? And I'll do this in the context of stochastic linear time invariant systems. I'll start, this is basically this averaging matrices and extended Kalman filter, the last 2 points. And I'll start by, first of all, the offline question. What if you have more offline data? So you build a Hankel matrix, you can use this now, and someone comes and gives you a lot of data. Or while you're running the system, you collect more data. What can you do with this extra data? In data-driven methods, usually more data is good. In machine learning, it's good. In adaptive control, it's good. Everywhere you look, more data is good. Paradoxically, for this method that I just described, more data is not good. More data is a problem. The obvious use you can make of more data is to enlarge your Hankel matrix. And because the rows of the number of rows in the Hankel matrix are fixed, is your horizons, how far you look into the past and into the future, so what you can do is add more columns to the Hankel matrix, which means you increase the number of decision variables, you have to take linear combinations of these columns, and you increase the number of degrees of freedom that you allow the outliers in the noise to exercise. So you basically make your problem difficult to solve and difficult to tune. So that's not very good. Okay. So what's the difference? Why is it so much more difficult with these methods to use more data? The key difference is data compression. If you do machine learning, you rely on, for example, statistical learning theory, finite VC dimension. Once you reach that, any data you collect over and above this complexity class where you're looking for just increases the confidence in the decision that you made within that complexity class. Okay. Same thing for system identification. You freeze your models. The more data you collect, you do, let's say, a least square fits, the smaller the variance is in your problem. Now, in our case, we don't have compression. Can we bring compression into the picture? Well, hold on. So, can you bring compression into this picture? Yeah, yes, but very simple idea. This is the idea of averaging. Basically, you look at the system. If you look at the Hankel matrices for this linear system with noise, they have this structure here, right? What you have on the right is some stuff you don't know. This is the state trajectory of the system. This is the noise trajectory of the system. The only thing you know is the input trajectory of the system. Okay, that you know, but these other things you don't know. What you know again is the matrix on the left. This is the Hankel matrix. That's the data you collected. You got this blue thing in between. This is a matrix that depends on the model. And this is a matrix that you don't know either because you don't know the model. So there's a lot of stuff you don't know and very few things you do know. Okay. So that's not particularly useful. But one thing you can do very easily is just take linear combinations of these things, right? You see, if you take linear combination of these things, the blue matrix in the middle remains the same. You just take linear combination of the things on the right. The middle thing you know. The X you don't know, it's a state trajectory, but if you take linear combinations of state trajectories, you get a state trajectory, so that's fine. If you take linear combinations of noise trajectories, if they are independent, you get a noise trajectory with smaller variance. So basically, if you take linear combinations of Hankel matrices, you get a valid Hankel matrix with lower noise. Okay? And that's basically the trick. Just reduce the noise. You can do that. You go, if you have perfect online data, for example, clean online data, noisy data, you average it, you get less noisy data, you get a picture that looks like this. By increasing the number of Hankel matrices you average, you reduce your noise, you improve your performance in the system until you reach this basically green line, which is the best you can hope to do. And you see this regularization parameter, the optimal regularization parameter going down, it suggests that you're actually getting less and less data, that you're getting better and better in your estimates. You can also make better use of online data. If you have noisy online data, it doesn't work quite as well to do averaging because you cannot do averaging on the noisy online part, which is the YDUD on the right. But you can try to do some kind of Kalman filtering. Kalman filter requires a state space model. You don't have one, but you have a predictor. It's implicit in your optimization problem. It's implicit in the solution of the quadratic program. And you know how to solve QPs. You know the solution is piecewise affine in the parameters of the QP, which is the data that you put in there. So you can use this to form an extended Kalman filter. A locally affine prediction with a linear readout gives you an extended Kalman filter. And this is what you get when you do that. You get, this is the Kalman filtered version, much better performance with respect to the noise. You see here, if you increase the amount of data that you use in the past, you get sort of better performance also if you don't use a Kalman filter, but with a Kalman filter, you can do it with a much simpler optimization. I'll leave you with this. This is again the slide on the remaining questions. I try to answer a couple of those very briefly in the last few minutes. And I'm looking forward to doing a bit more work on this with my colleagues under this new project that we're starting now in Switzerland, this NCCR automation funded by the Swiss National Science Foundation. Yes, thank you very much for being here and for listening to my story. I'll be very happy to take your questions.
John, thank you very much for that great talk on data-enabled predictive control. I think there are a number of questions, and David, I'll pass it over to you for maybe summarizing a few and asking maybe 2 or 3 of those.
Sure, thanks, Claire. And thanks, John, for a great talk. So I've tried to keep track of everything, all the questions. The first question is, given that the state is not explicitly computed with this approach, can you somehow include a cost or constraints on the state?
Not directly. There is a surrogate state, which is this past sequence of inputs, but there is no immediate state concept. It's sort of even, a change of coordinates in the state you won't be able to see because you don't have access to the state. So it's not easy to directly include constraints on the state. You can include constraints on the outputs that you can measure, or by making these fancier linear combinations that you think have something to do with the state, but because you don't have a state representation, you cannot do constraints directly on the state.
Thank you. And how do you ensure in practice that the probing signal is persistently exciting?
You can, persistent exciting is a rank condition on a matrix. Some matrix has to be full row rank that you construct with the input that you apply. This is failing that condition is a fragile condition. So if you apply noise, almost surely you can get a persistent exciting signal. Many other signals are persistently exciting. PRBS type signals are persistently exciting. Even impulse responses you can make persistently exciting if you know what you're doing. So that's a relatively easy condition to meet, practically as well as theoretically.
And lastly, do you gain anything if you sort of are in the large data regime? Like, do you converge to having anything interesting?
In the big data regime, this is what I was trying to hint at. It's very difficult to incorporate more data. The only thing we thought of is this averaging of Hankel matrices, which actually works quite well. Convergence there in the average, you basically filter out all the noise and you get sort of like low large number type convergence. This is one of the things that we're thinking about also for the online system. Can you do something recursively where you make use of this data and you update this model recursively, as you would do in adaptive control, for example? But I won't stick my neck out because we really don't have the answers to what's going to happen there. This is sort of what we're hoping to do in this new project that we're starting with Florian.
Great. Thank you so much, John, for your talk. And thanks to both of our speakers, Leslie and John, this morning for starting off day 2 of the conference. We're now going to transition into a break for about 11 minutes. We'll start again at 10 o'clock Pacific time with our first session of contributed papers of the day. I think during the break, we're just going to try to cycle through all of our at the screen, all of our folks who've contributed to the conference, just to additionally thank them for their work in the conference. Okay, so see you in about now in about 10 minutes.
Welcome back, everyone. It's my great pleasure to chair this session where we're going to go through paper presentations, where we're going to focus on techniques for learning for control, looking at very different aspects of the problem, ranging for learning policies with robustness guarantees, policies for multi-agent systems, policies that are based on convex optimization, or also learning to model attackers. It's going to be an exciting session, and I'm looking forward to an active discussion. Please remember to post your questions during the talks, and then Lucas Heving will help me moderate the Q&A. That I'd like to start introducing our first speaker. If you can share the slides, Kaiqing Zhang, who's presenting joint work with Binhu and Tamer Basar on policy optimization for H2 linear control with H infinity robustness guarantee, implicit regularization, and global convergence. Stage is yours.
All right, thanks. Can you see the screen? Okay, great. Thanks for the introduction, and thanks to the organizer for organizing this wonderful conference. It's really an honor to be the first presenter of this wonderful session. And today I'm going to talk about policy optimization for H2 linear control with H infinity robustness guarantee. So as we all know that reinforcement learning has achieved tremendous successes in many sequential decision-making tasks and also some continuous control tasks. So one workhorse or algorithm is direct policy search, or we call it policy optimization methods. It is very nice because it can easily handle the case with large or even continuous spaces by using function approximation for the policy class. And also as an iterative algorithm, it's very easy to implement, and it's more scalable to high-dimensional control systems compared to some other standard control solvers based on solving linear matrix inequalities or solving semi-definite programming. In addition, it better enables the data-driven or sample-based local search method, as some of the talks have already mentioned. There are some great examples of policy optimization methods that have achieved state-of-the-art performance in different decision-making and control tasks. Let's take a closer look at what policy optimization is doing. It essentially reduces this control problem into an optimization problem. More concretely, we propose to view it as a constraint non-convex optimization problem. So indeed, in general, many control problems can be formulated this way, where the K here is some parameterized policy, or we call it controller, and J is some objective we want to optimize. And it's in general a non-convex function of this control parameter K. And the calligraphic K here represents the set, the constraint set that this parameter K belongs to. And sometimes this constraint set can be implicit. Oftentimes, it is very important. Let's take linear quadratic regulator, LQR, as an example, which is possibly the most well-studied example in the joint area of learning for control. Here, the JK becomes a long-term additive cost. And we know that the policy can be parameterized by a game matrix K. And right now, the big K here denotes the set of all stabilizing controllers, because otherwise the system will blow up and the cost is not even well-defined. Although people sometimes don't write out this constraint set explicitly, but this is very crucial to consider. And also we know that this big set is in general a non-convex constraint set. Okay. There's some other examples of this calligraphic case, such as the boundedness of the norm of the parameters, or some other safety constraints on the state, which can also be translated back into some constraint we need on the controller. So in this work, we advocate another very important constraint in control theory, that is robustness constraint. Beyond stability, robustness is another very important theme in control theory, and it is especially important in learning for dynamics and control, L4DC. More specific, we want to find some controller that is robust to a certain level of disturbance or model uncertainty. So this is a very classical paradigm. P is the plant we want to control, and K is some feedback controller. Putting them together, we have this nominal system G. Delta denotes some perturbation onto this nominal system. And this G delta model is very classical. It covers many robustness considerations in control theory, including the most commonly studied case with parametric uncertainty, where we have delta A, delta B on this model parameter A and B. In addition, it also covers or can be used to model the cases with time variant parameters A, B, or even time variant delay control cases. In addition, it can also be used to model the dynamic uncertainty, we call it, which can be used to model the uncertainty caused by the unknown model order of the nominal system, which is a very challenging uncertainty. Then under this general framework, one key notion that to help us to characterize the robustness is entry-infinite norm. It's a core concept in robust control theory. Intuition comes from this very famous Morgan theorem saying that if we can allow this transfer function to have H-infinite norm smaller than some gamma, constant gamma, then this G delta interconnected system is input-output stable if this perturbation has this L2 to L2 gain smaller than 1 over gamma. In other words, the intuition here is that if we can somehow impose a constraint on this controller so that the H-infinite norm is smaller than gamma, then it gives us a certain level of strong robust stability. By saying strong, we here only want to emphasize that it covers many different kinds of uncertainty, as I just mentioned. And as gamma goes to infinity, this reduces just to the stability region I just mentioned for LQR problems. Now, in this work, we aim to address the following open but challenging questions. The first one is whether it's possible and how to enforce or maintain robust stability in policy optimization RL methods during learning. Interestingly, this was something mentioned by Professor Zhang in last year's L4DC regarding how to develop RL methods to maintain the stability or robustness of a system, especially when we want to develop the algorithm for actual control systems. And also, we are interested in establishing the global convergence guarantee, if any, of these policy optimization methods in learning for robust control. To this end, we start with a very basic setting in control theory that is linear dynamics with state feedback. So our paper covers both continuous and discrete time settings. And here I will focus on the discrete time one just for simplicity. Here X is the state, U is the input, and W is some exogenous input, or you also call it a disturbance, and Z is the output. Then in this case, the H-infinite norm is defined as L2 to L2 operator norm from this signal W to Z. Then the problem we are interested in solve is to minimize certain cost subject to this robust stability constraint. The JK here is usually an upper bound of the actual H2 norm from this W to Z. And two commonly used objectives are listed here, especially on the left-hand side. This objective, the PK here is the solution of some Riccati equation for fixed controller K. You can see if you allow this gamma go to infinity, this equation, Riccati equation, reduced to the Lyapunov equation we used in the policy evaluation step for solving LQR problems. Therefore, the left-hand side, this first objective will reduce to the exact H2 norm that you want to minimize in solving LQR problem. In that sense, this problem is a classical formulation of optimal control with additional robustness considerations. One thing to highlight here is that this model is very general. It covers the risk-sensitive linear controller as an example, specifically the linear exponential quadratic Gaussian LEQG problem. There was some very interesting literature by Glow and Doi saying that this feasible set of this LEQG problem indeed preserves certain level of H-infinite norm constraint. Therefore, all our results here will also apply to the risk-sensitive linear control using RL methods, solving that using RL methods. We established some new results on this interesting connection in our paper as well. Also, this model covers some other classical robust control models, such as the maximum entropy / H-infinite norm control, and also the zero-sum linear quadratic dynamic games. We'll have more detailed discussion on this unification in the paper. And also, I draw the parallel here to compare our problem with LQR problem, where we don't have this robustness constraint here. Then how to solve it. So this figure illustrates the different landscapes of solving these two problems via policy optimization method. On the left-hand side for LQR problem, we call this objective to have some certain some kind of coercive property, saying that if this iterate K is approaching the boundary of this stability region, the cost will blow up to infinity. However, unfortunately for H2 H-infinite mixed design, we don't have such a property. Indeed, we formally state that, of course, these two problems are both non-convex, but also our problem does not have this coercive property. Therefore, unfortunately, unlike LQR, we cannot use this objective to help us regularize the iterate, cannot ensure the feasibility of our iterate. Because right now, even for LQR problem, any decent direction of this objective will ensure the next iterate will remain in this feasibility region. But for our case, even if you are decreasing your cost, you may still go beyond this robust stability region. Then how to ensure that during the learning? So on the algorithm side, we propose to use policy gradient methods motivated by this seminal work by Fazer et al., which analyzed the policy gradient methods for solving LQR problems, which are policy gradient methods, natural policy gradient methods, and Gauss-Newton methods. The later two have both have very nice interpretations in different contexts. So that's why we use this very natural and standard algorithm to solve the problem. And then we define something called regularization. We call this iterate is regularized if it is confined inside this robust stability region. This can be, of course, made explicit if we are able to do projection onto this set. However, this kind is general non-convex and it's not computationally tractable to do that. Interestingly, we show that the natural policy gradient and Gauss-Newton methods implicitly regularize the iterates, meaning that they preserve the robust stability automatically. You don't need to do additional things. More formally, we have the theorem saying that if you choose the step size of these two methods to be this way, it's very simple. It can be a constant step size. Then the previous iterate of satisfying this robust stability will imply the next iterate is doing so too. This means that although the general descent direction of the objective cannot preserve robustness, but certain local search directions will help us. So this slide is only for those who are interested in the a little bit technical details. In this proof, we resort to some linear matrix inequality-based technique, which is motivated by the proof of this very famous boundary lemma, which connects this robust stability to the existence of a solution of some Riccati equation or Riccati inequalities. And then we construct the solution of this strict Riccati inequality by a perturbation theory of some Riccati equation. With this regularization results in hand, we can then establish the global convergence result. We show that these two methods will converge to the global optimal of this problem with the sublinear rate. This controllability assumption of this pair of matrices was also made in the original paper that formulated this discrete time mixed design problem. One thing to highlight here is that this condition holds automatically for the risk-sensitive case, meaning that we show that for the risk-sensitive LEQG problem, landscape is very nice. As LQR, there's only one local optimal, and there's no local optimal. Also, in contrast to LQR, where the objective has a global gradient domination property, in this case, the gradient domination property only holds locally. That's why we can only have a local faster rates, which is a linear, could be linear or even superlinear. But globally, we can only show sublinear rate. So we have also done some simulations, which I may not have time to talk about in detail, but essentially it validates our theory saying that the algorithm not only converge, but also preserve a certain level of robustness along the way during during learning. One thing to highlight here is that for the vanilla policy gradient, which we do not have theoretical guarantees for now, we indeed observe the case where with infinitesimal step size, it can easily go outside this stability region, robust stability region, although eventually it converges. This implies that this algorithm may not be a good choice. This specific searching direction may not be a good choice if you want to do this. To conclude, in this work, we take an initial step toward the theoretical understanding of policy-based method in learning for robust control, and more general for the robust risk-sensitive RL in general. Also advocate to embrace the classical, or at least not to abandon the classical H infinite norm constraint to characterize a strong robustness for RL in continuous tasks. And we show that in this linear control case, this robustness almost comes for free. We have also discussed some future work in the end of our paper. Several things to highlight here is that in this work, we focus more on the non-convex optimization landscape of this problem. And right now, we focus on establishing the sample complexity of this problem, which is challenging because the naive zeroth order method will fail. We don't allow the perturbation of the controller at all directions. Also, we're interested in the landscape of this H infinite optimal control problem. We want to find the most robust controller. A higher level question is we always need to keep in mind we need to enforce this safety or robustness constraint on the fly for all the other model-free RL in general. Although we show for linear control case, it can be satisfied almost for free. So that's all I have. Thank you.
Thank you so much for the great talk. Lucas, do you have the questions from the YouTube chat?
Yes, thank you very much for the talk. There's a question from the YouTube chat asking what happens if you don't have access to exact gradient evaluation? For example, if you have gradients from data in a batch setting.
Yes, that's something we are establishing the model-free setting. So this is challenging. That depends on how good that estimate of this policy gradient is. We see that in this robust stability case, this robust we call robust stability margin is very sensitive. It could be very small. Therefore, if the estimate of the policy gradient is very bad, then it can easily go outside the region. Therefore, the naive zero-order method shouldn't be considered here. We need some other gradient estimate to help us do that.
Great. And maybe one more question. You mentioned that the H infinity case would be the holy grail. Can you maybe comment on some of the challenges that you have in attacking this problem?
Yeah, that's a very nice question. So for the H infinity optimal control problem, you want to minimize H infinity norm, but that problem will become non-smooth with respect to the controller parameter. So that's one of the key challenges. And also the landscape is not clear yet because we don't know whether this the place where subgradient equals to the zero belongs to a subgradient would be a good point that implies any global optimality. So it's I think the key challenge here comes from the non-smoothness.
Great. Thank you very much again. With that, let's move to the next talk. If you could stop sharing, then the next speaker can start. Our next speaker is Guannan. He's going to present his work on scalable reinforcement learning of localized policies for multi-agent network systems, which is joint work with Adam Wierman and Nali. Stage is yours.
Can you see the screen?
Yes.
Thanks for the introduction, and thanks for the organizers for organizing this workshop. This is joint work with Adam Wierman and at Caltech and Lina from Harvard. Given the recent success of the reinforcement learning, in this talk, we are going to investigate the application of reinforcement learning in control of large-scale network systems like traffic network, communication networks, or energy networks. Such large-scale network systems can pose unique challenges for reinforcement learning. For example, one of the core challenges is the scalability issue, as the nodes in the network can be hundreds, if not thousands of them. In this talk, we will try to apply reinforcement learning to these network control settings and to tackle these challenges by exploiting the network structure. So as common in reinforcement learning, we start with a Markov decision process, but over a network now. Consider a network of nodes, and each node has a local state Si that is in a finite state space, and a local action Ai that is in a finite action space. The global state is then the tuple of the local states, and the global state space is then the product space of the local state spaces. And similarly, the global action is the tuple of the local action space, is the product space of the local action spaces. The structure that we consider in this setting is a common one in network systems, that the interaction among the nodes happen in a local manner. To state this intuition in the language of MDP, it means that the state transition factorizes, and the node i's next state only depends on its current state, its neighbor's current state, and its own action. So in other words, the interaction only happens in a local manner. We also assume that each node is associated with local state reward Ri, which depends on the local state and the local action. The global state reward is an average of the local state rewards. In this setting, the goal of reinforcement learning is to find policies that maximizes the objective. Here we focus on the class of localized policies, meaning that each agent's action only depends on its local state. And objective is the common infinite horizon discounted reward, which is common in reinforcement learning. So immediate challenge here is the scalability. If we directly apply standard RL algorithms, it typically involves storage and estimation of the Q function, which is essentially a table of the action and a state. And here, because our state is a tuple of the local states, and our action is a tuple of the local actions, this essentially involves enumerating all possible combinations of local states and local actions, whose time-space complexity is exponentially large in the number of nodes, which is clearly not scalable. There's been some attempts in the literature that tries to reduce the computation burden. Typically, the method is to use some low-dimensional structure to approximate this Q function. For example, by using linear function approximation, which projects this Q function into a low-dimensional subspace, or we can use neural networks to do the approximation. However, such approximation will lead to an optimality gap, and the optimality gap will depend on the approximation error, which is typically unbounded. And further, there are some results showing that such MDPs with product state action spaces are in general intractable from a computational complexity perspective. But at this point, all the methods I have introduced treats the underlying network as a black box and haven't utilized any model structure yet. Whereas our problem has a rich structure. We have this local interaction structure. So the question we are going to ask is that, is it possible that we exploit the network structure, that we can design scalable algorithms that finds a near optimal localized policy? Our answer is affirmative to some extent. To give you a preview of the results, we show that by exploiting the network structure, we can find a near optimal policy with complexity scaling with the state action space size of local neighborhoods as opposed to the global neighborhood. So to put our results in context, this stands in contrast to existing methods whose complexity is either exponentially large in the number of agents or has a unbounded optimality gap. Now I will explain our approach. We return to the Q function. We parameterize the policy by parameter theta, and for this policy, the Q function is defined to be the infinite horizon discounted cost started from this state action pair. And because our reward is an average of the local rewards, we can plug this in to show that the Q function is an average of the local Q functions, which are essentially Q functions for the local rewards. But these Q functions, these local Q functions, are still exponentially large tables because of the coupling among the agents. Our main idea is basically to reduce the dimension of the local Q function by using the local dependence structure. So given the local dependence structure, it is natural to think that nodes far away from each other might have diminishing effect on each other. To formalize this intuition, we let NIK to denote the k-half neighborhood of a node I. And then we define the exponential decay property, which means that in a Q function, if we change the state action pair outside of the k-half neighborhood, then the change in the Q function is small and it's decaying exponentially in K. While this is a definition, we also show that if the rewards are bounded, then the exponential decay property will automatically hold with the decaying rate rho upper bounded by gamma, the discounting factor. And this is a consequence of the local dependence structure, the discounting factor, and the mixing rate of the Markov decision process. Given the exponential decay property, the Q function's dependence on faraway nodes are very small. This naturally leads us to define the class of truncated Q functions, which only depends on the local neighborhood and ignores the influence from outside the neighborhood. And more formally, the truncated Q function is defined to be a weighted average of the real Q function, where the influence from outside is averaged out by arbitrary weights. And we show that under the exponential decay property, which always holds, this truncated Q function is a good approximation of the full Q function, and the error is decaying exponentially in K. This means that even for a small K, we can get a very good approximation where the dimension of the truncated Q function is much reduced. We then combine this idea with the actor-critic framework. Given the objective as a function of the policy gradient theorem gives the policy gradient, and which depends on the Q function. We simply replace the exponentially large Q function with our much smaller truncated Q function. And then we look at the actor-critic framework, which uses TD learning to get the Q function and then to gradient descent. We simply replace that with the truncated Q function and the truncated policy gradient to arrive at what we call the scalable actor-critic method, which uses TD learning to estimate the truncated Q function and then calculate the truncated policy gradient and then do gradient method. To summarize a bit, the main idea so far is that we start from a local dependent structure to develop the exponential decay property, which then motivates us to develop the truncated Q function, which is then used in actor-critic methods to develop our scalable actor-critic algorithm. So since our algorithm only uses truncated Q function, its complexity is much reduced than the full Q function. But what about the optimality guarantees? We show that our algorithm can find a policy whose gradient can be bounded by two terms. The first term goes to 0, where the second term is the steady-state error due to the truncation of the Q function. The important thing to note is that the steady-state error is decaying exponentially in K. So even for a small K, this is close to a local minimum. But in the meanwhile, the complexity scales with only the state action space size of the K-half neighborhood, which can be much smaller than a full state action space size, at least when a graph is sparse. This shows that at least when the network is sparse, our algorithm can do RL in a scalable manner by exploiting the sparse local interaction structure. Beyond the results here, in our most recent work, we are also able to extend our results to go beyond just local interaction structure. And further, we extend our work in the direction of average reward, which is basically the reward in stationarity, which is a more challenging problem. And finally, I would like to give a simple example based on multi-access wireless communication to illustrate the method. So in the multi-access wireless communication model, there's a set of users and there's a set of access points. And at each time, each user will basically receive a packet into its queue with a certain arrival probability. And you can choose to send its packets to a nearby access points. And the access point will transmit the packet with a certain probability. And upon a successful transmission, the user will get a local reward 1. However, if two users send to the same access point at the same time simultaneously, there will be a collision and neither packet is sent and neither user will get any reward. And so in this setting, the average reward it can be interpreted as the throughput of the system. And clearly, because the collision can only happen in a local manner, this is a local interaction structure, and we apply our method to this system. And we compare our method with the benchmark based on the Aloha protocol. So our results show that at least in this simple setting, our approach can outperform the Aloha-based benchmark, despite our approach does not have knowledge about the model parameters, where Aloha does know the model parameters. And with this, I would like to conclude. The main point of this paper is trying to do reinforced learning in a scalable manner for network systems by exploiting the network structure. And this is the list of references, including the L4DC paper and 2 recent follow-ups. And I'm happy to answer questions. Thank you.
Thank you so much for the great talk and for staying perfectly in time and leaving time for questions. Lucas, do you have the questions?
Yes, thank you very much for the talk. So I have a question. You said that the exponential decay is in part due to the discount or the discounted cost. Can you comment on how you can move then to the average reward case that you consider?
Yeah, so that's a great question. For the average reward case, this problem actually in the worst case can encode certain NP-hard problems. NP-hard problems like graph coloring or K-set. So in the worst case, it will not hold, and this problem is in general intractable, which is consistent with the complexity results by T-cyclics. What we do is that we identify a rich subclass of the problem. As long as the problem has sufficient randomness in its transition kernel, then the exponential decay property will show that it will still hold. And it is in that case, we can do something for the average reward case. Yeah.
Great. There are questions on YouTube now. One question is asking how much conservatism you introduce by relying on local state information of each agent only, and if you could extend it to using information of your neighbors as well.
Oh, I understand the question as if the focus on the local policy. So actually, recently in this more recent work, we actually consider a more general policy where each user can use information, the states of like its neighbors, or even like more than neighbors. We will show that there will be some improvement, but we haven't characterized the exact, exact trade-off or improvement as compared to the pure local setting. But this is a very interesting question, and we are interested to see what is the exact role of this more information.
Maybe one more quick question on YouTube. Is rho a function of your network topology?
Yes, so rho is always overbounded by the discounting factor, and discounting factor is not related to the network topology. It's not related to the network topology, but rho can be strictly less than the discounting factor, and the exact rho will depend on the network topology. Yes.
Great. Thanks again. And there's more questions on YouTube. Please post them in the on Open Review to discuss further.
Okay,
with that,
thank you.
We'll go to the next talk. That is going to be presented by Shane Barratt. It's joint work with Akshay Agrawal, Stephen Boyd, and Bartolomeo Stellato on learning convex optimization control policies. Thank you.
Great, thank you. Hello to everyone on the live stream, and thanks for joining. I'm going to talk today about our paper, Learning Convex Optimization Control Policies, which is joint work with my amazing collaborators, Akshay Agrawal, Stephen Boyd, and Bartolomeo Stellato. And the paper is about a method for tuning parameters in a control policy to achieve good values of a performance metric. We'll see that it turns out that most control policies used in practice actually correspond to solving convex optimization problems. And we'll talk about a gradient-based method for automatically tuning such policies. We do, however, assume knowledge, or at least an approximation of the dynamics. And that's an important thing to keep in mind. So first, I'm going to talk about what I mean when I say a convex optimization control policy and the problem setup. Our setting is going to be a pretty standard control problem where you know the dynamics. And we use standard notation. So X is the state, U is the input, and W is the random disturbance, all indexed by the time period T. The function S is the state transition function, which we're going to assume is known. So now that we've specified the dynamics, we need a policy, or a mapping from states to inputs. We're going to consider a very specific policy, a convex optimization control policy, which from now on we'll refer to as a COCP. We call our policy phi, and phi at a state X is given by the solution to this general convex optimization problem on the right that depends on the state X and the parameter theta. We're going to assume that this problem is convex, meaning Fi are all convex in U, and Gi are all affine in U for each X and each theta. The vector theta are the parameters that we're going to tune, which adjust the policy by changing the shape of the objective and the constraint functions. I'll note that phi depends on theta, but we're going to suppress this dependency to lighten up the notation. And it might be obvious to some already, but most continuous control policies actually have this form. And COCPs also have some pretty attractive properties compared to other parameterized control policies. For example, when the convex problem that to be solved is well chosen, the policy is at least reasonable for any choice of the parameter value over the allowed set. Whereas for other policies like neural networks, that might not be the case. And also with COCPs, it's very easy to specify constraints on the input and other structure on the policy, which might be hard to do with other parameterized control policies like neural networks. So with the dynamics in the policy in hand, the next step is to define the cost or objective. Given a COCP, sequences of the state and input are actually random. They form a stochastic process. Therefore, we're going to consider length T trajectories denoted X, U, and W, and judge a COCP by its average cost over these trajectories. averaged over the disturbance W and the initial states X naught. And worth noting here is that in contrast to traditional stochastic control, we make no independence assumptions on W and also no assumptions on the separability of psi. Next, I'm going to go into some concrete examples of COCPs. The first is the optimal dynamic programming policy. We're going to make a couple of assumptions on this slide, namely that the cost is time separable and that the disturbance at each time is independent of the disturbance at other times. These are the traditional stochastic control assumptions. And under these assumptions, as t tends towards infinity, an optimal policy has the form of just minimizing the expected value of the current cost plus the cost to go of the next state. And when f is affine in x and u, and g is convex in x and u, for every w, it can be proven that v is convex. So the optimal policy in this case is a COCP, because addition, expectation, and affine precomposition all preserve convexity. A notable special case here is LQR, or the linear quadratic regulator, where the dynamics are affine and the cost is a convex quadratic. In that case, the cost to go function is a convex quadratic. And so the optimal policy is the argument of the expectation of the sum of two quadratics, which is just a quadratic, and the argument is linear, leading to the linear policy that's optimal for LQR. For more general convex costs, however, it's hard to find the cost to go function v, even though we know a priori that it's convex. So when this is the case, this kind of leads us to the approximate dynamic programming, or ADP policy. When we don't know v, or the exact functional form of v, we can replace it with an approximation v hat. And here, when g is convex in u and f is affine in u for all x and w, and additionally v hat is convex, this is also a COCP for the reasons explained on the previous slide. Here, the cost g, the dynamics f, and the cost to go v hat can all depend arbitrarily on the parameter theta, and that's the thing that we're going to tune in this policy. And ADP policies are used everywhere in practice. I'll note that for the sake of space, I've omitted the model predictive control COCP, but it's pretty self-explanatory what you would do there, and more details on that can be found in the paper. Next up is the learning method. That is, how do we actually tune the parameters in a COCP so as to minimize the expected cost? In general, this problem is highly non-convex and difficult to solve exactly. So it's reasonable to consider using maybe a derivative-free method like random search, grid search, or an evolutionary method. But in practice, these can be very slow, especially when the parameter is large. So instead, we're going to consider a gradient-based method, which for many problems has observed to be much faster than derivative-free methods. A crucial observation in this paper, in this talk, is that the solution to a convex optimization problem is often differentiable in the parameters that appear in the problem. The consequence of this is that a COCP is often differentiable in x and theta. The fact that you can differentiate a COCP with respect to its parameters comes from a series of papers and software implementations that I and several of my collaborators have developed in the last year or so. I don't have time to fully go into the details, but this basically means that you can export a convex problem to PyTorch or TensorFlow, and it's fully differentiable. And just an important note here is that we perform exact implicit differentiation in contrast to unrolling the steps of a numerical solver. And so this means that it also works for problems with non-smooth objectives or constraints. So if the costs and dynamics are also differentiable, which they often are, then we can compute the gradient or an approximation of the gradient of the objective with respect to the parameters using backpropagation through time or just the chain rule. And then having done this, we can use this projected stochastic gradient method to update the parameters in our policy until we converge. And one thing to note is that even when the COCP is non-differentiable, you often still get a descent direction, which is just like the case for training neural networks, which can be trained and are trained using gradient descent, despite only being differentiable almost everywhere. So how we actually implement this is using our package CVXPy layers, which takes CVXPy problems in Python and converts them into fully differentiable PyTorch and TensorFlow layers. Then we use PyTorch for the chain rule to implement the backpropagation through time, and also to implement the gradient method that updates the parameters. And you can find our CVXPy layers package at this GitHub link here. Now I'll describe two numerical examples. 3 other numerical examples can be found in the full paper online on arXiv. And the examples that I'm going to describe here are a box-constrained LQR problem and a supply chain problem. We first consider a pretty standard LQR problem, but where the input is constrained to be in a box specified by Umax. We consider here an ADP policy using just a convex quadratic approximate cost to go, where we've dropped the constant terms. The parameter here is theta, which is just the square root of the quadratic coefficient in the cost to go. And we do this so that this COC, or the objective here, is always convex for any value of the parameter theta. So we don't need a constraint on theta. And we compare this policy trained using our gradient descent method to a sophisticated upper and lower bound that you can compute using linear matrix inequalities, or LMIs, which can be found in this reference here. The policy for the upper bound, in fact, has the exact same form as the ADP policy here, but it finds theta by solving an LMI. And here we show the average cost throughout the course of learning. We can see that the COCP converges to roughly the same cost as the policy that achieves the upper bound. Since this problem is challenging to solve exactly, we don't really know where the true optimal cost is, outside of the fact that it's somewhere between 11 and 13. But we can see that our super simple gradient-based method does just as well as the super complicated LMI-based construction of the ADP policy. And this result, I think, is particularly interesting because while the LMI method is highly specialized for its particular box constraint problem, our method is not. It works for much more general problems. And at least in this case, it works just as well as this very sophisticated LMI method. The next example is a supply chain, more practical supply chain optimization problem. You have a single good supply chain with n nodes, and the state consists of the quantity of the good that you hold at each node, the price of the good that you're going to purchase from the suppliers, and then the demand for the good at the consumers. The action is the quantity that you're going to ship in between the nodes, the quantity that you're going to buy from the suppliers, and the quantity that you're going to sell to the consumers. And here we're going to assume that we know the price at which the consumers are going to purchase the good are. So the dynamics are linear, and they simply update how much of the good you hold at each of the nodes depending on the action that you took. And A is just a matrix which determines how your action adjusts the holdings. So the next price and the demand are going to be just randomly sampled. And your goal here, we're going to make the goal to maximize profit. So we're going to make the cost simply the negative profit. And additionally, in our cost, there are various constraints. For example, you can only ship a certain amount through each link, and you can't ship more than you have on hand. And we're going to consider a very simple ADP policy where we've again dropped the constant terms, and where the cost to go function is a function of the amount of goods you hold at each node at the next time step. And the constraints are the constraints from the previous slide. The parameters here are S and Q, and everything else we know. We consider a very simple example with 4 nodes labeled 1 through 4, 2 supply links going into nodes 1 and 2, and 2 consumer links that go out of nodes 3 and 4. The average supplier price at node 1 is lower than that of node 2, and the consumer price is higher at node 4 than node 3. Therefore, the optimal policy is to buy a bunch from node 1 when the price is low, send it to node 4, and sell it there for the high price. Here we show the normalized average shipments for the untrained and trained policy. As you can see, the trained policy buys a lot at node 1 and sells most of it at node 4. So it looks like it's doing something reasonable. And we also observe that the cost is much lower. So the summary of this talk is that we can tune COCPs efficiently using gradient descent and just simple off-the-shelf packages. COCPs make it super easy to enforce constraints or other structure, which could be hard with neural networks. And we also have a couple more examples to or applications to vehicle control and finance that can be found in our paper. So that concludes my talk. Thank you. I'll take any questions.
Thank you, Shane. Lucas, I'll hand over to you.
Yes, thank you for your talk. So maybe you can clarify. You said in general you don't assume IID disturbances W, which also I guess also means that you can treat the case of kind of parametric uncertainties. But then in the dynamic programming based solutions controllers, you often need this kind of IID assumption. Can you maybe comment on that?
Yeah, so I think that's a great strength of this method. You don't have to make any of those assumptions. You basically write a simulator that can have, disturbances that depend on previous disturbances, and then you just tune the policy to do as well as possible under in that simulator or under those assumptions.
And there's a question on YouTube asking if the choice of parameterization is similar to a choice of architecture in a neural network.
Yes, it is. That is similar, but it's more of a, it's different than the choice of architecture for a neural network. It's kind of like you say what you want to be minimized as opposed to what the policy is going to do. So that has some parallels to declarative versus procedural programming. And for some problems can be much more natural to say, what do I want my policy to be optimizing versus what do I want it to be doing?
Maybe a final question. Have you compared this to kind of gradient-free methods? And how do you think it compares?
We haven't, but yeah, that would be a good comparison. Yeah, I suspect that this would be much faster because it's utilizing that curvature information in updating the parameters. So it would probably require at least a few orders of magnitude less evaluations of the cost function.
Great. Thank you again, Shane, for the great talk. And we'll then move over to the last talk of the session, which is presented by Xuezhou Zhang, which is joint work with Xiaojin and Laurent Lessard. And the title is Online Data Poisoning Attacks, so looking at a slightly different aspect of learning control. Stage is yours. We cannot hear you. I think you still have to unmute yourself.
Can you hear me now?
Yes.
Okay, perfect. Yeah, thank you for the introduction. So this is joint work with Laurent Lessard and my advisor, Jerry Zhu. So in this work, we try to build a connection between control theory and adversarial machine learning. As summarized by one of the anonymous L4DC reviewer, our work poses the learning problem as a dynamical system and study its robustness to adversarial inputs using techniques from control. So with that, let's get into it. So in this work, we study a problem called online data poisoning attacks. But let me first introduce the data poisoning attack problem in the traditional offline setting. In this setting, we assume that the environment first generates a dataset D. For example, D can be a set of images. This dataset is then assumed to be fixed and known to the attacker. Next, the attacker comes in and adds some kind of perturbation delta to the dataset. For example, it can be a small pixel-wise perturbation on the existing images, or it can be injecting a small batch of new images. But either way, eventually the learner receives a perturbed dataset D prime and performs learning. Here we assume that the learner is performing some kind of parameter optimization with a particular loss function L on the parameter theta. Given this interaction protocol, the attacker desires two things. First, he wants the learned model to satisfy certain properties. Various properties have been studied in the literature. For example, in what's called a targeted attack, the attacker wants the learned model to be close to a target model. In what's called a version attack, the attacker simply wants the learned model to be far away from the ground truth model. Or in the recently popular backdoor attack, the attacker wants the learned model to make certain prediction on a predesigned pattern, Z star. For example, he might want a face recognition classifier to always predict positive whenever a purple sunglasses appear in the image. But the point is, all of these properties can be represented by a loss function on the model parameter. Besides that, he of course also wants the perturbation to be small to stay undetected. Taking these two objectives, we can write the data poisoning attack problem as a bi-level optimization problem, where the attacker wants to find optimum perturbation delta to minimize a weighted sum of these two objectives, subject to the learner's learning dynamic as the constraint. So this is the classic formulation of data poisoning attack in the offline setting. Now let's look at the online setting, where everything becomes sequential. At time step t, the Wierman now generates a data point zt from some distribution p. For example, it can be an image of a panda. This process becomes stochastic, and the data point that will be generated in the future is not known to the attacker. Similarly, next, the attacker adds some perturbation to the current data point. For example, it can be some small pixel perturbation to the panda image. Given this perturbed data point zt prime, the learner now performs a learning update. For example, if the learner's doing online gradient descent, f will be one gradient step with respect to some loss function on the parameter theta t. Similar to the offline setting, the attacker desires these two things, and one can define a running cost as a weighted sum of these two objectives. Our key insight in this work is that the online data poisoning attack problem can be casted as an optimal control problem. In particular, the dynamical system is the joint system of the learner and the environment. The state is the combination of the learner state, which is the learner's model parameter, and environment state, which is the current data point. The action, of course, is the perturbation the attacker generates. And system dynamics involves both the learner's dynamic, which is the learning update rule, and the environment's dynamic, which is the stationary distribution P. With all of the above, we can define the optimal attack problem as an optimal control problem, where the goal is to find an optimal attack policy phi that minimizes the infinite horizon cumulative attack cost with an optional discounting factor. We denote V phi P as the value function under this objective. Now at this point, we can almost claim problem solved if the attacker knows everything. But in practice, he often doesn't. In particular, what if the attacker doesn't know P? Well, we know that it's not hard to get an estimate P hat of P from data. Then we want to know how well can the attacker do with P hat instead of P. Our next result shows that it can do reasonably well. So theorem 1 says, as long as the running cost is bounded and the one norm distance between P hat and P is smaller than epsilon, then if the attacker performs the attack using an optimum policy with respect to P hat rather than P, the additional cost it suffers compared to the optimum policy as the most a constant times epsilon. This is great, but how many data points do we need to get a good estimate of P? Our second corollary discusses a special case where P is a multinomial distribution. In this case, if P hat is estimated based on n samples, the optimality gap is at most on the order of 1 over square root n. For those of you who are familiar with reinforcement learning, this result maps to a 1 over epsilon square pack bound, or equivalently a square root t regret bound. These are the optimal rates achievable in the tabular reinforcement learning setting. Here we show that in the special case, we can achieve the same rate despite that we have continuous state and action space and complicated system dynamics. In the general case, we can use kernel density estimation to get a rate that will be slightly worse than a 1 over square root n rate, and it's going to depend on D, which is the model, which is the data dimension. So these are the theoretical results. Now empirically, as learning continues, we know that the attacker will keep observing more samples from P and constructing more accurate estimates of P. This motivates us to use model predictive control. So in model predictive control, at time step t, the attacker will do 3 things. Right? He will construct a new estimate P hat t of P using the newest data and compute the optimum policy under P hat T. Then he will perform a one-step attack using this policy. What remains to be answered is how we compute the optimum policy under a distribution P hat. In this work, we present two approaches. First, we can just throw it at a deep reinforcement learning algorithm, and it will eventually return a policy. In this paper, we use deep deterministic policy gradient, or DDPG. Secondly, we can try to solve a deterministic version of the optimum planning problem. In particular, we can first sample a sequence of H data points into the future from the distribution P hat T. We can then solve an optimum planning problem where we try to find a sequence of perturbation delta that minimize the cumulative attack cost for the next H steps. Finally, we'll perform the attack using the first perturbation in the return sequence. Given these two approaches, we now present some real data experiments. In our experiments, given a dataset D, the stochastic data sequence is generated by uniformly sample from D. We consider two victim learners in our experiments, the online logistic regression, a supervised learning algorithm, and the online k-means clustering, which is an unsupervised learning algorithm. Finally, we consider three baselines. The first is what's called a null attack baseline, where the attacker simply does not add any perturbation. This serves as an upper bound on the total attack cost. The second baseline is the greedy attack baseline, where the attacker only optimizes the current steps running cost, GT. Finally, we have what's called a clairvoyant attack baseline, where the attacker is assumed to know the true data sequence in advance, and thus the name clairvoyant. As a result, it can directly solve for the optimum perturbation sequence using nonlinear programming. This serves as a lower bound on the total attack cost. So here are some selected results for attacking online logistic regression. In the graph, we're plotting the cumulative attack cost as a function of T. From the graph, we can make several observations. First, the null attack, which is the blue curve, and the clairvoyant attack, which is the the purple dash curve, they indeed form upper and lower bound on the attack cost in all three experiments. Secondly, greedy attack does not work well, and it's only slightly better than null attack on all three data sets. Now let's compare the deep learning approach, the DDPG method, versus the optimum planning approach, the NLP method. So we can see that DDPG performs reasonably well, but it doesn't quite match with the optimum performance. As for NLP, on smaller problems, which is the breast cancer data set here, where it can afford a large enough look-ahead horizon, it can almost match the performance of the clairvoyant attack. However, on larger problems where it cannot afford a large enough horizon, its performance degrades and becomes worse than DDPG. So here's a summary of comparison between DDPG and NLP. In terms of performance, as we have seen just now, DDPG can't quite converge to the optimal attack policy, whereas NLP can nearly match the optimal performance as long as it's given large enough planning ahead horizon. However, one advantage of DDPG is that it actually computes attack policy, which can be used for more than one steps, whereas NLP must be recomputed every step and incur high computational cost. Finally, DDPG does not require an analytical form of the learner's dynamic F and can treat the learner as a black box. On the other hand, NLP must require the analytical form of the learner's dynamic F in order to perform gradient calculation, for example. So lastly, I want to end my talk with some questions that we did not answer in this work, but can be good directions for future work. First, in this work, we assume that the data distribution P does not vary over time, and is the only unknown quantity to the attacker. The question is, what if P becomes non-stationary? What if the P will vary depending on the learner's action? Or what if the learner's dynamic is also unknown to the attacker, or the current modeled parameter theta t is not fully observable? These are all very realistic assumptions. Secondly, in light of the dynamical system view of the data poisoning attack problem, what does it mean for a learner to be robust? Does it mean that an induced system is not fully controllable, or does it mean something else from the control perspective? Lastly, can we generalize the optimal control approach to other learning settings, such as active learning, bandits, and reinforcement learning? Finally, here are some follow-up works on connecting adversarial learning and control from our group. Feel free to check them out. Thank you, and that's the end of my talk. I'm happy to take questions.
Thank you very much for the nice talk. We have time for maybe 1 or 2 questions.
Yes, thank you very much for the talk. I have a question. So if you want to apply this kind of MPC nonlinear programming approach, that kind of means that you need a continuous and probably differentiable cost function. This might be hard to apply to some other problems then, right?
Yes, yes. So as I hinted on here, the optimal planning approach requires everything probably to be continuous and differentiable in order for the nonlinear programming solver to deal with it.
And there's another question on YouTube. How do you feel about the defense side? Do you think that we can also use optimal control to defend against attackers?
Yes, that's precisely my second follow-up question here. So there are existing defense angles from robust statistics, but that's not aligned with this optimal control view, right? So here I was hinting on, we have to think about what defense means from a new angle. If we think about the learning process as a dynamical system, what does it mean even for the learner to be robust? I was thinking maybe it means something about the controllability of the system, but we're not sure yet. It's a very good direction for future work though. Yeah, very interesting question.
So I think related question on YouTube, you assume that the learner is oblivious to the attacks.
So we observe the learner to
framework where you could have maybe a game setting where you also have a learner which defends against attacks.
Yes, yes. So in general, it'll be, if the learner is aware of the fact that there's an attacker, then there will be a 2-player game, sequential game between the learner and the attacker. That's also a very interesting framework to study.
Great. With that, I'd like to thank all the speakers of the session again. Very nice talks. We will now go into a short break for about 12 minutes. So we come back here at 11:15 Pacific time for another session with presented papers, now focusing a little bit more back on the learning for dynamic side. Looking forward to seeing you all back.
Thank you.
All right, welcome back to our next session. We'll get started. This session will be moderated by Sarah Dean. Our first talk is by Yue Sun from University of Washington, who will discuss finite sample system identification.
Thank you. Hi, everyone. I'm Yue from University of Washington. Today, I'll talk about my joint work with Samet and Maryam about the regularization method in linear system identification. Okay. We face a case that we can only observe the input and output and have no idea about the state space of a linear system. However, based on assumption that the system is usually simple, we use a Hankel nuclear norm regularizer to indicate that the system is low order. Low-rank Hankel matrices are applied in many areas, such as in our work, identifying a low-order LTS system, or the moments estimation, equivalently recovering some of exponentials applied in tomography and geophysical inversion, or in video imprinting, which means that there are missing frames from a video and one recovers them using some underlying structures. Regularization is also commonly used for super resolution. Here, Chen Chi paper assumes sparsity of single frequency signals and encourages it by the low-rank Hankel matrices. Low-rank Hankel matrices have been used a lot previously in the classical work. For example, people project onto a set of low-rank matrices by SVD and single value truncation, such as these works. More recently, people discovered the power of nuclear norm regularizers and use nuclear norm regularizers in optimization objective. But these work only study algorithms and implementations, and we want to study the statistical performance of the regularization algorithms, such as the sample complexity or recovery errors, which will be defined later. So such bounds are recently studied for least squares or unregularized methods. The first batch of works investigates the regime when the state of the original or closed loop system is observed and linear regression is applied. The second batch investigates input-output system with direct least squares on input-output map or filters for pole aggregation, Maryam stable system, and so on. And compared with the amount of recent work on least squares, only this Tsai paper works analyzes the Hankel nuclear norm regularization for a super resolution problem, but it is worst case bound and does not cover all interesting error metrics. Hence not fully comparable with least squares papers. So we hope that the regularizer method should provide good bounds on the recovery error, and we'll show later the good guarantee for the number of output samples while it is easy to pick the model order. We denote the input, state, output, and noise as U, X, Y, and Z. When we say the system is order R, we mean that the state can be represented as a vector of size at least R, and they evolve as this expression. When X is dimension R, A is R by R matrix. For simplicity, we present a Xuezhou system, so B and C are R by 1 and 1 by R. Then we denote H as this, which is the impulse response we talked about, and the system order is the rank of Hankel matrix defined below. However big size you make it, the rank is at most R. Then we say the system order is R. We do not know system order in advance, so we set the impulse response to be length 2n minus 1 and assume that n is large enough, say n is bigger than R. So now that we have two quantities, a small number R, the unknown true system order, and a big number n, the dimension of our estimation. This extends to block Hankel or MISO and MIMO case. Also, we can write a map between input and output as a convolution, and we can also consider a noise Xi being ID over time. We feed in design input U, which is properly random, collect Y and recover H from U and Y, the input and output. We denote SNR by the average power of input over noise. There are two data acquisition methods. For regularization, we talk about the left one here, and we observe one output and we restart the system and collect the second rollout. It's called multiple rollout. The right one here is discussed in recent least square or unregularized paper where the input is continuously fed in and all output from a trajectory are collected. We use sample complexity T for the number of output observations, also the number of equations we use for regression. Now we state our algorithm. The variable is h prime, and we have two terms in objective, a squared error term and a regularization term. The h expression is Hankel matrix, or a linear transform of the variable. If lambda is 0, then it's least square. If lambda is not 0, then the regularizer encourages low rank structure. Now, we recover the impulse response by this. How do we justify the recovery? We use two metrics, the L2 error of impulse response or the spectral norm error of the Hankel. The first one is studied more in least squares work, but we emphasize the second one, which is very important because it is related to an error of recurring system ABC matrices. The remark is that Hankel spectral error upper bounds the L2 error, but we will prove that their recovery error are the same. Here is our theorem. We hide the log terms here. The second line is an easy generalization of size bound, and the first line is our main theorem. The first remark is that least square is solving linear equations. So since the number of unknown is n, we need at least n equations to find a meaningful solution. But with a regularizer that indicates low rankness, the number of equations needed is system order R smaller than n. A remark is that least square impulse response L2 error in Oymak Z paper is tied up to log factor, and we prove that when T is R squared, the Hankel spectral error bound is same as the least square impulse response L2 error. Note that the spectral is an upper bound of the L2 error, so they are essentially roughly the same. So this means that we do not need a very accurate guess of system order when setting up the problem. We will show what it means for implementation later. Another remark is that although in least squares, ID inputs are typically used in our regularization work, if system order is sufficiently small, for better sample complexity, we need to use a random input with its power shaped. We can theoretically prove that with input shown in the first figure, the sample complexity is in R and only log in N, whereas we prove that with ID input, the sample complexity is suboptimal and to the power 1/6. Now, we also refine the least square analysis without regularization. Here we list two least squares papers, and they use different algorithms. The Oymak OZ bounds impulse response L2 error are optimal, but their Hankel spectral norm error bound proven is suboptimal. The Sakar-Rachlin Daley paper proves optimal Hankel spectral norm error bound, but loses in sample size. So we ask if we can get both sample complexity and Hankel spectral norm error bound optimal. So we have the following theorem in terms of spectral error, which is optimal. The takeaway is this: Hankel spectral error is almost the same as impulse response L2 error. To summarize, we have this table. In this work, we study two algorithms, with or without regularization. Least square error is optimal in terms of n and t and sigma. This regularization we gain in sample complexity while error metrics are preserved. We think that with regularization, we think that with regularization, the error dependency should also gain, but due to the scaling in our proof, it is not achieved at this moment. Finally, we show how regularization benefits in implementation and practical performance. We experiment on DAISY data, and it is single rollout. First, we need to tune the parameter. In regularization, we can fix the problem size n and change weight lambda and the solution. Hopefully, it's automatically low order. In least square, we have to change the problem size n and hope it matches the order. We can see the validation error both go down and up, and we can pick the model with the smallest validation error. This is easier in regularization since we can continuously change lambda compared to change n within integers, and there is a wide range of lambda that gives small validation error. These figures show how Hankel single value of two recurrent models with the problem dimension. When they both approximately recover the system with enough observations, the regularized recovery shows a bigger single value gap, so it is very easy to see the system order. Now we come to prediction. We use 50 data to train a Tibetan Hanko. It has 19 unknown parameters and 400 validation data. We can see that with scarcely enough data, the regularized one has good performance, whereas least square misspecifies, and you can see that the validation trajectory is totally wrong. Here are the conclusions. Empirically, nuclear norm regularization provides more robust recovery, not only shown in our experiments, but also known for long in other literatures. We also proved the error guarantee of regularization algorithm and match with recent least square result, and also refined suboptimal least square proof for a fair comparison as well. Finally, the future directions, we hope to get better understanding of the empirical behavior, such as the spectral gap or sensitivity of the regularization parameters, etc., and investigate if error bound or statistical rates can be improved. And that's all. Thank you. Yeah, the reference.
Thank you. We have time for questions.
All right, I guess I will start with a question. Thanks for the talk. That was great. My question is, what are the challenges for going from this sort of multi-rollout analysis where you have one sample per rollout to like a single rollout?
Yeah, so actually for least square, there, if you know, like their bounds are roughly the same up to log factor, but for regularization, it is more difficult in terms of the matrix analysis because you want to get the restricted isometry for the regularization term, and that is like a little bit difficult for the single rollout matrix, and that we haven't known, and we are interested in like investigating its future. Yeah, thank you.
Cool. I guess another question is, I think you mentioned that the resulting bounds you get do depend on n to some extent. So like there is like it seems like you'd like to choose the smallest n that's bigger than r, but not by too much. Can you comment on that a little bit?
Oh, actually, we don't know r, so maybe we just use a very large n like for our estimation. But like in least square, maybe you have to have like enough equations or sample complexity because n is big and you solve these linear equations, so you have like the same number of linear equations. But in regularization, actually, it is only logarithmic in n. So if the true r is system order r is small, then the number of observation needed is not that much. So that is the advantage of regularization.
I see. That makes sense. And I guess in terms of choosing the regularization parameter, do your theoretical results rely on choosing a particular like value of that parameter, and then how does that translate into practice?
Yeah, yes. So in terms of like writing down the theorem and have a like provable guarantee, there is a specific lambda that the weight that gives you the like good performance. But in actual implementation, maybe if you have a good guess of like how big the noise is, you can do that. If you don't, then you can just implement it and see the validation curve and pick the best lambda. And this is comparable with compared to this least square, it is easier because the curve is flat. So yeah, if you can see the curve is more flat, though, so picking the best validation is just roughly simple. Yeah.
Great. Thank you very much for a great talk. We're going to move to our next speaker, which is Tassos Giannis. I probably just butchered, unfortunately, the last name. Sorry, Tassos.
It's fine.
How do I say it the right way?
The name, Tsiamis.
Tsiamis. I was not that far off. All right, so Tassos is going to talk about the sample complexity of Kalman filtering when you don't know your system.
Can you see my slides?
Yes, they look great.
Okay, so thank you for the introduction. So in this paper, we are dealing with time series data. Think about, for example, the path of the pedestrian or financial data or the position of a drone. And we are interested in the prediction problem, where we want to see what will happen in the future by filtering past data. And this is a very important problem in many decision-making applications. Think, for example, the autonomous driving car problem, where we want to avoid pedestrians. And if we know the system that has generated the data in an ideal world. We know how to filter the past data in order to predict. But in practice, of course, the system might be unknown. And in this case, we need to learn how to predict from data. Now, in order to do so, there have been two main learning architectures, the model-free one and the model-based one. As the word says, in the model-free, we want directly from data to learn a filter in order to predict. While in the model-based one, we first learn a model based on system identification, and then we design a filter. Those two approaches have different advantages. Very briefly, the model-free architecture might be more suitable when we want to predict complex systems. By complex, I mean, for example, a system which is impossible to have a model in the first place. On the other hand, for safety critical applications, it might be more suitable to use a model-based architecture, because it allows for robustness guarantees. And also the model-based architecture is more modular in the sense that we can use the filter design step as an additional degree of freedom that we can tune. Now in this paper, we will focus on the model-based architecture, where traditionally the certainty equivalence principle has been applied. This principle states that the learned model is ideal, but this assumption in general requires a large amount of data, let's say infinite data, mathematically. For this reason, in this paper, we introduce a new paradigm for prediction, where we take into consideration the fact that the number of data might be finite, as captured by this number n. As a result, the system identification will return a learned model, which is not ideal, and will have an error, as captured by this epsilon of n. And also, similarly, the filter design step will return a suboptimal filter. So the question that arises here is, how does this learned model affect my prediction performance? What is the impact of having finite data? And if we can have any guarantees? In order to answer this question, we first have to solve two sub-problems. First, we have to see how fast the system identification error decays as we gather more and more samples. And for this step, we will use tools from high-dimensional statistics and tail inequalities for self-normalized martingales. Next, we have to analyze the filter design step and see how the uncertainty of the model affects the prediction performance, and also how should we do filter design in order to mitigate this uncertainty. And for this, we will use tools from classical estimation theory, but also modern tools from robust control, like the system level synthesis framework. To bring back this question, it is possible to obtain guarantees for the problem of having an imperfect learned model. And in this paper, we performed the first such analysis. And this is made possible because we bring together tools from both worlds, from both learning and control. Of course, there has been related work. Finite sample complexity of system identification has been studied before, but these guarantees that exist are not compatible with the filtering problem. Robust filter design has also been studied, but not in relation to having a learned model. And finally, a very related problem is that of the sample complexity of linear quadratic regulator. See, for example, the papers from Ben's group. Although LQR and optimal filtering are dual when we know the system, if we don't know the system, then they are not dual. Now let me go through the formal description of the setup. Consider this following linear system, which is only driven by noise. Now, if we know everything, if we know AC and the noise statistics, then the optimal filter is known to be the Kalman filter, where here K is the Kalman filter gain. Now, if we don't know the model, then we perform system identification and filter design, and we obtain the following predictor, where here, these A and C we get from system identification step, and these parameter cell are the filter gains, which are to be designed. Now, this data-based filter will be suboptimal, and to measure this suboptimality gap, we take the difference between this filter and the Kalman filter. And this is the price of not knowing the model. And the question is, how does the finite number of samples n affect this suboptimality gap? The assumptions that we consider are in general standard. We assume IID Gaussian noise. We assume that the system is observable. All the parameters are unknown apart from the system order. Also, we assume that the system is stable, which means that the spectral radius is less than 1, which seems to be a necessary condition for offline architectures. If we have the slightest model error, if we don't have stability, then eventually the suboptimality gap will blow up. Now let me go through the analysis step by step. First, we analyze the complexity of the system identification step. We use a subspace system identification algorithm based on least squares. And the analysis is based, as I mentioned before, in tools for self-normalized martingales. And we obtain the following guarantees. With high probability, the model errors decay with the order of 1 over square root of n, where n is the number of samples, and some system-specific parameters. First, we have the condition number of the noise. This captures intuitively the fact that noise both excites the system, because we don't have inputs here, but also obstructs identification because it introduces errors. And then we have this term sigma, which in some sense captures the least observable mode of the system. It's linked to some singular values of some matrices. Also, I don't mention it here specifically, but explicitly, but the recovery is up to some similarity transformation. Next, we analyze the filter design step, and we analyze two designs. First, the certainty equivalent design, where we directly use the learned parameters without any filter design. And then we analyze a robust version of the filter, where we use the system level synthesis framework in order to design those gains L. As I mentioned, in the certainty equivalent filter, we just use whatever parameters the system identification returns. But because of errors, this might not always work. In the following theorem, we prove that if a robustness condition is satisfied, then the suboptimality gap decays nicely. And this robustness condition can be satisfied if either the system identification error epsilon is small, or the true closed loop matrix A minus KC has good stability properties. By this, I mean that the spectral radius is far away from 1, far away from instability. This condition cannot always be satisfied. And in fact, it might be possible that the certainty equivalent filter can be close to instability, which means that the learned closed loop system has spectral radius close to 1, which is bad for performance in general. For this reason, we might want to consider an alternative filter design, a robust one, to improve the stability margin. And in this paper, we consider the SLS framework, where we reparameterize the filter gains L in terms of some new variables. So the predictor, this is the block diagram of the predictor, and before we wanted to design those gains L. But with this new reparameterization, we optimize directly over the maps from y to x hat, which is the map phi of y, and the map from Ly to x hat, which is phi of x. Now, the details can be found in the paper, but the bottom line is that with this reparameterization, the problem becomes more tractable and convex. So in the end, we obtain the following optimization problem, where we minimize the distance from the certainty equivalence filter subject to robustness constraint. And this constant here controls the trade-off between how much we trust the certainty equivalence filter and how much we care about robustness. Theoretically, we obtain kind of similar guarantees with a certainty equivalence filter. So we have a similar robustness condition qualitatively. But the important distinction is that even when this condition is not satisfied, then we have guaranteed stability margins on those closed loop responses, which lead to improved performance, as we will see later in the simulations. Bringing everything together, we can obtain end-to-end guarantees for the suboptimality gap. And with high probability, this gap decays with the order of 1 over square root of n. It's interesting here that if we improve the stability properties of the true system A and the true closed loop system, this might improve the filter design step. It might, but this does not necessarily help the system identification step, because by, for example, choosing a smaller A, we might make the system less observable. So this, the least observable mode, let's say in sigma, might decrease. Based on some Monte Carlo simulations, we can verify that for both filter designs, the suboptimality gap decays as fast as the 1 over square root of n. And now we can see for the high error cases, the robust Kalman filter seems to be performing better. But this becomes more clear if we look in the following figure. where we condition on the event that the certainty equivalence filter is close to instability. In this case, we can see that the robust filter performs better. To summarize, we offered a new paradigm for prediction over learned models and performed the first finite sample analysis and obtained end-to-end guarantees for two filter designs, the certainty equivalent filter and the robust filter. Now, going forward, we would like to generalize these ideas to the closed loop systems where we both have prediction and control. Also, it would be interesting to obtain uncertainty bounds, which are richer than just norm poles. And finally, we would like to consider guarantees for online learning architectures. With that, I would like to conclude my talk, and I will be happy to take any questions.
Thank you, Tassos. Great talk. We have time for some questions.
All right, yeah, that was a great talk. Thank you. I have a question about sort of these unknown noise covariances and how you're sort of seeming to implicitly learn that by identifying the optimal common filter parameter approximately. Can you expand a little bit more on that?
Yeah, that's a very good question. Actually, in this kind of problems, let me go back to the system identification diagram. So as you can see, we can not only learn A and C, but implicitly there is information about the noise covariances, and we learn the Kalman filter gain directly. So all the information about the covariance is included there. And in fact, because there are infinite equivalent systems with infinite possible covariances, we can only learn this one, which corresponds to having, actually, let me show you here. Yeah, you can learn this one here, where the noise is replaced with this innovation error, let's say. And you learn this K instead of learning the covariances.
Cool, yeah, that's interesting. I guess sort of related is you mentioned that even though LQR and common filtering are sort of dual problems when everything is known, that no longer holds when things are unknown. And related to that, there's a question from the chat, which is that in LQR, we sort of know that there's this lower bound of 1/√T. Would that bound apply in this setting, or like what are the differences basically between the learning LQR and learning?
Yeah, thank you very much for this question. So yeah, they are not dual because first of all, in the partially observable case, we have an ill-defined state space. So I didn't explicitly mention that, but when we have partially observed systems, we can have infinite state representations. So that's a very important difference. And any similarity transformation can change this representation and can still explain the data that we have. And obtaining one such realization is a non-convex problem when we have partially observed systems. Now, another difference is exactly as I mentioned, that from data we can learn directly the Kalman filter gain. While in LQR, we need also some exploration, to obtain some of this information. So in some sense, obtaining the gain is easier in the Kalman filter case. Now, this also goes to the last question. Although for this kind of offline architecture, we have similar bounds with LQR, 1/√N, let's say. Now we proved recently that in the online case, we can actually prove logarithmic bounds, which shows in some sense that there is some gap between Kalman filter and LQR. And it seems to be easier to do the filtering. So yeah, we haven't looked at lower bounds, but maybe that would show there.
All right, great. I think, do I want one more question time?
One more question would be great.
Yeah, so I guess, is there some notion of observability that affects the bounds in this analysis directly?
Yes, so here. So this sigma is, let's say, it's related to the least singular value of an observability matrix and also of a Hankel operator, which implicitly depends on an observability matrix. So yeah, the observability is important here.
Okay, great. Thank you so much, Tassos. Really fantastic. We're going to now move to our final speaker of this session, Jasmine Sekon. Jasmine, if you could share your slides. see if this works. Beautiful. Thank you so much. And Jasmine is going to talk about joint trajectory prediction modeling vessel intents.
Yes, thank you, Ben. So I'll briefly first begin by explaining the problem at hand here. So consider we have multiple agents trying to navigate in a crowded environment. In this case, we're modeling vessels, so our agents are ships. And assuming we were trying to navigate this particular ship through this crowded environment, and it is important for us to know where the other ships are headed at future time steps so that we can negotiate a safe collision-free path for ourselves. Now, a similar problem exists in other multi-agent scenarios. For example, if for pedestrians that are trying to navigate through a very crowded train station or say urban road traffic, where for safe navigation, you require the ability to anticipate where the neighbors are headed over a certain future time steps. So our goal basically is to predict the future intent for all these agents that are trying to navigate safely in a multi-agent setting. And now intuitively, we could use LSTMs to do this because of their sequence modeling capabilities. So we could simply have an LSTM that models trajectories for each of these agents. For example, here we have an LSTM-based encoder-decoder architecture where the encoder has access to the XY coordinates or the positional information that is related to this particular agent. Now it encodes that information and the decoder uses this encoded information to then predict the coordinates at the future time steps. But there's a problem with using this particular approach. The problem is that in multi-agent settings, every agent's trajectory is influenced by its neighbors' current positions and their expected future intent. So for the pedestrian scenario, assume I'm a pedestrian and I'm trying to navigate through the lobby of Grand Central Station here. I see another person that is approaching me from front. Now, just to respect that person's personal space or simply to avoid collision, I would digress from my original path a bit, just to avoid collision, right? And then I might not do that for every other person in the scenario. And I also might respond to some people more than I respond to other people, which would depend on how they influence my trajectory. So the problem is that conventional LSTM-based approaches cannot, one, model this spatial influence, and two, they cannot incorporate this towards predicting intent. So the basic goal of our spatial attention mechanism that we propose is one, to model the spatial influence agents have on each other, and two, incorporate this influence towards predicting intent at future time steps. So going back to our application domain, which is ships, I like to first introduce a concept called ship domain. So when ships approach each other, they keep a minimum area around them clear of other ships, and this region is called the ship domain. So for example, if we are interested in predicting the future trajectory for this vessel right here, so V1, so V2, if it is within this region, which is called the ship domain, it tends to have a spatial influence on V1's future trajectory. Now, if there's another vessel that is at the same distance as V2, but at a different orientation, just depending on how this ship domain is edged out, it would probably not have a spatial influence on V1 at all. And again, out of all those vessels that actually do affect V1's future trajectory, some might influence it more than others, simply depending on orientations. Then we try to use this concept of ship domain towards computing the influence a neighbor has on an agent at a certain time step. So here we have a vessel V1. We are interested in predicting the future trajectory for this vessel. And then we have a neighbor V2. So the influence of V2 on V1 at T is modeled using this particular equation, where this weight W is used to quantify the spatial influence V2 has on V1. So based on this orientation, we also define a distance-based parameter called S, which is unique for each orientation. So just for this orientation, if V2 is at a distance that is greater than this particular distance parameter, it tends to not influence V1 at all. However, if it is within this region, so if the distance is less than S, it tends to have a spatial influence in V1, and its influence is inversely proportional to its distance from V1. So if you look at it carefully, what S basically models is the ship domain, and which is the concept that we talked about earlier. And one key point of our model is that we do not use any pre-existing knowledge for ship domain or any other methods. We simply treat it as a trainable parameter. By treating it as a trainable parameter, we mean that we let the model infer this parameter from observed data or the training data. This is our high-level proposed model architecture. So we basically use the same encoder-decoder-based framework. And then we also use a spatial attention mechanism to incorporate the spatial influences at each time step in both the encoder and the decoder. The way we do this is, if at a certain time step t, we have access to the spatial situation at that particular time step, so how the agents are oriented with respect to each other. This might either be in the encoder side of things, so an observed spatial situation, or it might be on the decoder side of things, so something that we predicted. So what we basically do is, from this spatial situation, we compute weights, so the spatial influence these agents have on each other, and then we compute the weighted hidden sum of these hidden states. This spatially weighted hidden state is basically what is fed to the LSTM at the next time step. Now, in conventional LSTM-based methods, we simply use this hidden state and we feed it into the LSTM at the next time step. By following our method, what we basically do is we give the LSTM access to not only knowledge about itself, so knowledge about the agent which it is trying to model, but also knowledge of the spatial context that has been perceived by the agent. So in addition to the spatial attention mechanism, we also adopt a temporal attention mechanism in the decoder. So by temporal attention, we mean at every time step, the decoder compares the spatially weighted hidden state that we got from the spatial attention mechanism to all the spatially weighted hidden states on the encoder side. So we can call these the observed spatially weighted hidden states. So it gives them a score based on similarity, and a more similar hidden state tends to influence the prediction at the current time step more. Now, how this would have real life applicability is, assuming I'm trying to predict intent for, say, a cargo ship, and at a certain time in the prediction time window, it encounters a fishing boat at a certain orientation. Then it tries to recollect from its observed experience that one time when it had encountered the fishing boat before, and now it knows how it's expected to maneuver, what its radius of turning is, and so on. So based on that particular spatial situation on the encoder side or on the observation side, we can then generate a more accurate prediction at the current time step. So more similar observed spatial context would basically be more influential towards prediction at the current time step. So putting it all together in the encoder-decoder based framework, we train, test, and validate a model on AIS data, which is basically automatic identification system and is positional data amongst other things that is transmitted by all kinds of ships at regular or irregular intervals. We use an observation time window of 5 minutes and we predict trajectories for every vessel in the frame for the next 5 minutes. In the course of minimizing error during training, our model also ends up training or inferring the ship domain parameter S that we introduced earlier. The metrics that we use to quantify the performance of a model are average displacement error, which is the mean error between the predicted trajectory and the ground truth, and also the final displacement error, which is the mean error between the final predicted destination at the end of 5 minutes and the actual final destination. To evaluate a model, we basically use this ablative setting where we use just a standard LSTM, an LSTM with only temporal attention, and an LSTM with only spatial attention, and then our model. So our model is not only able to predict very accurate trajectories, it is also able to predict a very accurate final destination at the end of 5 minutes. This is the ship domain or the S parameter that a model ends up learning after training on observed data. So like we said, we consider S to be unique, or the domain parameter, for every 60 degrees of bearing and every 60 degrees of heading. So it learns this parameter, and this is an example of how the learned ship domain parameter can cause a neighbor to have very different spatial influence simply based on its orientation and the learned parameter. So in this case, the size of the blue circle that pops up is basically proportional to the influence this particular vessel has on its neighbor at that particular time step. And just trying to break down this complex learned parameter. If we have a vessel V2 that is trying to maneuver around V1, so as its orientation changes around V1, the learned domain parameter that is learned by the model, it changes. And then as its distance changes, the computed spatial influence changes. So if you look at it, it kind of makes sense because V2 tends to have a larger spatial influence when it's in line of sight or approaching V1. And as soon as it is out of line of sight, it has little to no influence on V1 at all, which is basically the size of this blue circle. So to conclude it all, what we propose is a spatially and temporally attentive LSTM-based framework that jointly predicts intent for multiple agents trying to navigate in a scene. Our model is not only capable of predicting very accurate future trajectories, it is also capable of inferring useful domain knowledge, which in this case was the ship domain parameter. So this kind of knowledge can then be transferred to other non-ML based domains. Although we use our model on vessel data or ships, it's a very general framework that can be applied to any other domains, so pedestrian intent prediction, urban road traffic, or aerial systems, and so on. With this, I conclude my talk. I'm open for questions now.
Thank you, Jasmine. That was a great talk.
Thank you.
You have time for some questions?
Yeah. Hi. Yeah, thanks. That was a great talk. I guess one question from the chat is just how do you actually train all these parameters? Like, is it all the ships at one time or sort of like affecting the training, or like how does that actually work?
So basically we use training data. So I mentioned that we use AIS data from Zone 11, which is basically the area around San Diego Harbor. So for simplicity, we divide the entire frame into grids. And then in each grid, we take about all the vessels and then jointly predict intent for all the vessels. So they're around 30 to 32 vessels.
Cool. I guess you mentioned that this is sort of a general framework, and it definitely seems applicable to a lot of sort of trajectory prediction, like multi-agent. What kind of things would you like imagine changing to be more specific to different settings, or like what was sort of specific to nautical settings here, if anything?
Yes, so the good point here is that we actually tried applying it to pedestrian intent prediction. And because of the learnable parameter that we introduced, we do not really need to make any assumptions, or we do not rely on any strict assumptions here that won't generalize in another domain. So it's a very general framework that we can basically apply to. So if you apply it to pedestrians, for example, the domain parameter would change accordingly. And so there are really no assumptions that we rely on that would change for another setting. So maybe what could change for, say, urban road traffic is that they have different kinds of agents. So you have cars, but you also have pedestrians, you have cyclists and skateboarders. So it would be nice to extend this framework to kind of include all the diverse agents that could be there, and then what all these agents with different dynamics, how they influence each other. So those could be nice correlations we could probably find.
Cool. I guess like maybe one last question is, I guess for if you have like one specific agent that you're planning for, maybe you don't have to predict every other agent with the same accuracy, right? There's some sort of differential like necessity there.
Yes, but I agree with that. And the point here is that if I'm predicting for myself, I need to have an accurate prediction for everybody around me to be able to predict accurately for myself. So it's kind of very, yeah.
All right, great. Thank you so much, Jasmine. That was a really great talk. Thanks to all of the speakers from this session and all of the contributed speakers. It was really fun to actually have contributed talks this time around. And I really feel like we saw a pretty wide array of really interesting new results in a space that's developing really quickly. So we're going to take our final break before our final keynote, which is Chelsea Finn, which is a really great talk, which will start at 12:15. I'm very excited to see that. And yeah, we'll hope you rejoin us then at 12:15. And until then, have a good few minutes off.
All right, welcome back, everybody. And it's a great pleasure to welcome and to introduce our final speaker for the conference, Chelsea Finn, who's an invited speaker to the conference. Chelsea is a professor in computer science and electrical engineering at Stanford, where she runs the IRIS lab. She's also part of the Google Brain team. Chelsea graduated from Berkeley, and she won the ACM Doctoral Dissertation Award and the C.V. Ramamurthy Distinguished Research Award, and was also named one of the MIT Technology Review 35 under 35 awardees. Chelsea works in deep learning algorithms for concurrently learning visual perception and control in robotic manipulation skills. She also works in inverse reinforcement learning to develop scalable acquisition of nonlinear reward functions. And she's done pioneering work in meta-learning algorithms in these contexts. So welcome, Chelsea.
Thank you, Claire. I'm excited to be here. Today, I'll be talking about extrapolation and how we might extrapolate by adapting. So as some high-level motivation, a big question that I'm interested in, that my group is interested in, is how we can develop broadly intelligent behavior through learning and interaction. And to study this question, a lot of our work actually looks at robots in the real world and seeing if robots can learn skills in the real world, such as using a spatula to lift an object into a bowl, playing with children's toys to place blocks into shape-sorting cubes, or to be able to place an object into a bowl after watching a human place an object into the bowl and show which correct target to place it into. Here are a few examples of some of the work that we've done in the past. And I think that studying robots in the real world is quite exciting because robots can teach us things about intelligence. In order to build general purpose robots that can operate in real world environments, they must be able to generalize across tasks, across objects, and across terrains and so forth. So with this in mind, what I'd like to talk about today is specifically on generalization, providing a perspective on generalization for control, because I think that is really one of the big bottlenecks in actually moving towards more realistic settings and towards broadly useful robots and broadly useful control systems. So when thinking about generalization, I think we often find ourselves in a situation that looks like this, where our training distribution looks like something on the left, and the test data distribution that we'd like to be able to handle looks like something on the right, something that's broader. For example, maybe our trained distribution is a robot trained in a lab environment or in simulation or something, and our desired test distribution is in the real world, where we want the robot to be able to handle many different types of objects, like many different types of spatulas, or be able to operate in many different environments. So this is kind of the problem that I want to talk a bit about today. Now, I think that a natural reaction to this problem is, well, I know how to generalize to this desired test distribution. I know how to use many different spatulas to lift an object. Can I build in my knowledge into the algorithm in order to help the algorithm and allow it to generalize? For example, maybe I know things about physics, maybe I should program a physics simulator and use that to give data to the algorithm. Or maybe I should build in my notion of objects into the algorithm, or build in some notion of equivariances, such as how the scene rotations in the scene may affect the rotations in the action space, for example. Or maybe I want to build in something in particular into the neural network architecture to encourage it to reflect some of the things that I think, the way that I go about this task. But I think that there are a couple challenges with this reaction and a couple problems. The first is that, well, while we humans are really good at generalizing very broadly, we actually don't know how we do it. There's a whole field devoted to this, the field of neuroscience and cognitive science. And while there's certainly been kind of progress in these fields, I think that these are still really challenging questions. And even if we did know how we did it, or even if we're pretty confident about the way that we do things in particular, I think that we also don't know exactly how to program in these kinds of notions into our systems. And this is kind of the approach that that symbolic AI methods have tried to do for a long time. Of course, I'm not going to end this debate with a single slide, but what I'd like to talk about today is if we can do better than this, and if we can extrapolate without trying to build in this kind of knowledge. And even if it is worthwhile to build in this kind of knowledge into the algorithms, I think the things that I'll talk about today will also be useful towards furthering the generalization of our systems. So the two kind of specific approaches that I'd like to talk about today is first, instead of trying to build things into our algorithm to enable it to generalize broadly, I think that if we want our agents to generalize broadly, we should try to train it on equally broad data. That is, try to expand the training distribution to be much broader and develop algorithms that can learn from these kinds of scalable broad data sources. So this is the first point. And then the second point is figure out what assumptions that we can make that will allow the algorithm to generalize further. For example, in machine learning, we often make this IID assumption, which is very convenient, but it's also a relatively weak assumption. And we may be able to leverage additional assumptions that can help us generalize beyond the distribution that we are trained on. Okay, so primarily in this talk, I'd like to talk about the second point here, but I would like to briefly touch on the first point too, because I think it's very important. And to think about how we might broaden the training distribution and why this is important, I think we need to look at what our data looks like when we're actually running reinforcement learning. And I'll focus on robotics because I think that this is an example of reinforcement learning in the real world. But I think that in general, the trend in robotics is somewhat reflective of some of the trends that we've seen elsewhere in control as well. So 3 to 4 years ago, in terms of kind of pushing the boundaries of learning for control, some of the work that we did looked like this, like the videos that I showed on the second slide. And in these experiments, in these papers, we were looking at a single object, a single task, and a single environment. And of course, there was also a breadth of other robotic reinforcement learning work that also had this very narrow scope. More recently, we've seen people start to expand the breadth of the data that they're training on, so that they're trained on many different objects, but still a single task and a single environment. And then even more recently, work at Stanford and work at Berkeley was also expanding to not just many tasks, but also not just many objects, but also many tasks, but still in a single environment. And these images are reflective of the kinds of data that were being collected in those papers. So it seems like we're certainly making progress in terms of the breadth of data that we're training our algorithms on. But what does data look like in machine learning? Well, if we look at basically the rest of machine learning outside of reinforcement learning, data looks a lot broader. It looks something like this. And this was not just recent, this is many years ago. And really the data isn't comparable even. The data that we see in machine learning have many objects, many tasks, many environments, many different viewpoints and lighting and so forth. And we've seen this in computer vision, in natural language, and speech, and so forth. So it seems like there's this huge divide between the kind of data that we're training on in reinforcement learning and the kind of data that the rest of machine learning is training on. And it also seems like if we could push ourselves more towards this broad, these broad data sets that machine learning use, we can also expect much broader generalization out of our reinforcement learning systems. Essentially, time and time again, we've seen that data scalability has a much more substantial effect on generalization than changes to the algorithm. And we've seen this with ImageNet, with recently GPT-3, and so forth. So how do we actually bring this benefit of data scalability to reinforcement learning and robotics? I think that to do so, we need to figure out how to leverage large and diverse data sets rather than just collecting our data in the loop of our RL algorithm in a lab. And we also need to build algorithms that can learn from those large and diverse data sets. And I think that many of the algorithms we have today aren't actually well suited to learn from such data sets. My lab has been doing work on both of these two axes that I'll just touch on very briefly before talking about how we can generalize beyond the data distribution. So first, on the aspect of leveraging large and diverse data sets, some students in my group have been looking at actually sharing data across institutions, which is maybe a strange concept in reinforcement learning, but it's a very common practice in the rest of machine learning. And to do so, we actually need to look at data across multiple robots. So inspired by this, we looked at data that looks like this, collected from 7 different robot arms at 4 different institutions, and looked at how we could potentially generalize to new robots and new environments by leveraging much broader data. And we've also recently been looking at learning from videos of humans. The internet is a vast source of humans doing various behaviors. And if we can figure out how to leverage videos of humans doing things, then maybe we'll also unlock a much broader source of data as well. Then in addition to leveraging large and diverse data sets, we've also been looking at building algorithms that can learn from such data sets. And in particular, I think that one direction that will be really important is the direction of batch offline reinforcement learning, where you learn from one large batch of data rather than collecting data in the loop of the learning process. We've been developing model-based offline RL algorithms, as well as model-free offline RL algorithms that can do well in this setting. And we've also been looking at offline meta-reinforcement learning algorithms, where you try to be able to learn from a batch of data from multiple tasks in a way that allows you to quickly adapt to a new task. Okay, so that is a very brief touch on the first point of trying to broaden the training distribution. What I'd like to talk about for the main part of this talk is figuring out how we might allow the algorithm to generalize further. And I think that this is really important because it addresses potentially a fundamental limitation of the kind of IID machine learning setting that we all know and love. And when we think about generating these assumptions and figuring out how we might generalize further and which situations we may want to generalize further, we're going to do so under the, when thinking about reinforcement learning in open world environments, where we essentially have a robot in a very large world. And this is like, for example, the real world. And this is a setting that demands broad generalization because the robot is never going to be in the same exact state more than once, and it needs to constantly be handling differences and changes in what it's seeing. And in particular, we'll focus on 2 aspects of this problem. One is being able to handle persistent, continuous shifts throughout the learning process that are somewhat smooth, such as night and day lighting, wind, user preferences, or the mood of your user that changes continuously on a kind of periodic basis. And then we'll also be looking at what happens when you want to be able to generalize to sharp changes in new situations. And this may be caused by major events, such as new demands of the user, or maybe the robot finding itself in a drastically new part of the world, such as in a new building, for example. Okay, and to be able to handle these 2 different situations, we will need to introduce additional assumptions. And our goal will be to make these assumptions mild, but also powerful in terms of what they're able to accomplish. Okay, so first let's talk about persistent continuous shift. Of course, it makes sense to first look at prior work in this area. And one notable prior work in this area is POMDPs, which can, of course, model these kinds of persistent shifts in the environment. Where there's many different sources of potential partial observability in the environment, and this kind of covers this general setting. But a downside with POMDPs is that they're perhaps too general in the sense that it may be very difficult to develop algorithms that can solve the full POMDP problem. Now, there's also been other works that try to generalize or make MDPs more difficult. This include Bayes adaptive MDPs as well as hidden parameter MDPs. And these formulations assume that there's some hidden parameters underlying transitions and rewards, and these hidden parameters are fixed within an episode. And they may also change across episodes, but they assume that the hidden parameters are stationary. So essentially at the beginning of every episode, this problem setting assumes that the hidden parameters are drawn from some distribution that's stationary, that's the same over the course of the learning process. And this doesn't allow us to study more non-stationary settings where things might be changing persistently through time. So we'd like to kind of develop a problem setting that's somewhere in between these 2. And so basically a problem setting that is as tractable or similarly tractable as Bayes adaptive MDPs or hidden parameter MDPs, but more tractable than something like POMDPs. So with this in mind, we developed the notion of a dynamic parameter MDP. Like a BAMDP or a HIP MDP, we're going to assume that there are hidden parameters underlying the transition and the rewards. And these are going to be fixed within an episode. But we're going to assume that these parameters can systematically shift across episodes. Essentially, that the distribution that these underlying parameters are drawn from is dependent on the parameters from the previous episode. And this allows us to capture some of the non-stationarity that we might see in, for example, real-world environments. So how well do existing algorithms perform in this kind of setting? This is the first question that we wanted to answer. So we'll start with just two pretty simple settings. One is a simulated Sawyer arm that wants to reach toward this object, and the goal position of the object is going to be shifting in a circle over time, and the robot won't be able to directly observe how it's shifting. And the second setting is this half cheetah agent, and its goal is to run forward, but at different velocities that shift over time and with varying amounts of wind that vary over time as well. And these are fairly simple control problems with the exception of the non-stationarity. And we find that existing algorithms like SAC and PPO and SLAC all perform quite poorly in these settings. In particular, SAC and PPO are two off-policy and on-policy model-free algorithms that are very common in the literature. And SLAC is an algorithm that can model latent variables and model some amount of partial observability using latent variables. But we find that when these latent variables are changing systematically over time, all three of these methods perform very poorly in comparison to an oracle, where the oracle gets to observe exactly how things are changing over time. So our goal is going to be to try to bridge this gap. To build a method that can handle this setting, we build upon the framework of reinforcement learning as probabilistic inference, which casts reinforcement learning into the framework of graphical models. And what we're going to do is we're going to augment these graphical models with a dynamic latent parameter, where essentially we have this latent parameter z, and we're going to assume that this dynamic latent parameter evolves over the course of subsequent episodes according to some transition distribution given by P of z prime given z. And one key assumption that we're going to make here is predictability, the sense that we're going to assume that we can predict, we have the ability to model and effectively predict what future z primes will be given what we saw in the past. And this will allow us, this key assumption is what's going to allow us to be able to handle the non-stationarity. So under this graphical model, if you want to maximize the likelihood of basically the variables of interest, essentially maximize the probability of your trajectories given the and optimality being equal to 1, you get a lower bound that looks something like this. This might look a little bit complicated, so let's break it down a little bit. Essentially, there's three main terms here. This first term is just saying that we want to be able to model the dynamics and the reward of the state and the reward R. The second term is saying that we want to be able to model the latent variable. So we want to be able to model what the z is for episode I prime, given the previous episode, and also given the given the trajectory that you have so far. And then this last term essentially just corresponds to entropy regularized reinforcement learning. So all of these things are things that we can optimize tractably. For example, the KL we can optimize with the reparameterization trick, and the others correspond to either a maximum likelihood problem or a reinforcement learning problem. And we refer to the kind of resulting algorithm from this as lifelong latent actor critic, in the sense that we have this latent variable that's changing over the lifetime of the agent. Okay, so if we take the two simple settings that we showed before and compare it to these existing algorithms, we find that if we anticipate and predict the non-stationarity, we can actually learn fairly effectively amidst this non-stationarity in the environment and perform significantly better than algorithms that don't take into account or can't essentially model this non-stationarity. We can also look at more challenging settings, such as this Minotaur robot that has a varying mass, or a kind of simple 2D navigation task where you need to collect objects with varying wind, and also no resets through the entire lifetime of the agent. So the agent is continuously learning without actually resetting at the end of each episode. And we find that, again, in these more complicated settings, we also see substantial performance gains from modeling the non-stationarity and anticipating what things will look like based on the previous episodes. Okay, so the takeaway here is that by modeling and anticipating change, we can learn amidst substantial non-stationarity in the reward and the dynamics. Okay, so now that we've talked a bit about continuous shifts, let's talk about more sharp changes and being able to handle very new situations. And in particular, we're going to assume that we have one training environment or one training MDP, which we'll denote as mtrain, and we have new test environments, which we'll denote as mtest. And you only have access to the training environment during training, and at test time, you're placed in this new environment that may have different dynamics or a different reward function. We'll assume that the state and action space stays the same. So for example, we'll first start with a situation in simulation, and then we'll also look at a real world situation. We may have this Walker agent that is trained in kind of a standard gym Majoko environment. And then we want to be able to extrapolate to test environments where there may be an obstacle in the environment, there may be force perturbations applied to the agent, or some of the joints may be disabled. So how might we go about this? One natural approach to trying to solve this is to use something like robust control, where you maybe introduce some adversarial perturbations to the agent in the training environment with the hope that this will allow it to become more robust to various perturbations in the test environments. And the benefit of this approach is that it can generate perturbed situations during training, which will allow it to be more robust to those specific kinds of perturbations at test time. But doing so may sacrifice performance if your ball of perturbations is too large. It does require an adversarial optimization, which may be a bit tricky to get to work well. And it may also not be possible to have some kinds of perturbations in the real world without having a lot of detailed human involvement in the process. So it seems like there's some limitations to this approach. So we'd like to develop another approach that can maybe make progress on this kind of problem. And our hypothesis is that reinforcement learning algorithms and policy learning algorithms are brittle because they learn exactly one solution to the training MDP. And if they instead try to learn and remember multiple solutions to mtrain, and if the solutions are diverse enough, then they may be able to adapt that solution set to the test environment with the hope that one of those solutions, or at least one of those solutions, works well in the test MDP. So as a very simple kind of illustration of this, say you want to navigate, you're the green agent, you want to navigate to the red circle. You learn, instead of just learning kind of the green path, which you would learn in standard approaches to reinforcement learning, you're going to try to learn multiple different solutions. And you may already actually encounter these solutions during the learning process, so this may not actually be that much more expensive. And you're going to try to remember these different solutions and be able to control which of these solutions you actually perform during training. And if you learn these this kind of controllable space of solutions, then if you're placed in environments where there's parts of the state space that there's an obstacle or the dynamics have changed, then it seems pretty likely that while some of your solutions may no longer be viable, in this case, for example, one of your solutions is still viable towards reaching the goal. And this is, okay, one question here is, okay, this seems like an interesting idea. Under which situations will we actually expect it to generalize to a test environment? So one really important assumption is we need to assume that we can adapt with a small amount of data to the test environment. And the reason why we need this is because we're going to be adapting our solution set. So we need to figure out, use a little bit of data to figure out which of our solutions is viable at test time. And then the second assumption that we're going to make is that changes to the environment are local. Formally, what we mean by this is that the optimal policy in mTest also does well in mTrain. And so things like an obstacle being present is local in the sense that there is a good solution to mTest that that also does pretty well in mTrain because going around this obstacle also does well. If the dynamics change more globally, then this condition would no longer be true. Okay, and so for example, under these assumptions, you may be able to accomplish few-shot robustness to local changes in obstacles, terrains, frictions, and so forth. Okay, so this is the general idea of what we're going to be trying to accomplish. Now, one important question is how do we actually learn multiple solutions? To do this, we're going to learn a controllable space of diverse policies that achieve a return within epsilon of the optimal return. We'll learn a controllable space of diverse policies by using latent variables, and we'll try to accomplish this latter part by using a constrained objective. More formally, we'll try to optimize an objective that looks like this, where we're going to be maximizing the mutual information between the state and the skill. This ends up looking like, this decomposes into the entropy of S minus the entropy of S given Z. This is essentially trying to learn diverse skills, but skills that are predictable given your latent variable. And then this term will encourage us to actually have a policy that, that satisfies the constraint in the top right. Then at test time, after we've optimized for this latent condition policy, we'll roll out K policies, each with a different latent variable, and return the policy with the corresponding latent variable that achieves the best performance. And we'll refer to this as structured maximum entropy reinforcement learning. So if we look at robustness to various situations such as obstacles, perturbations, and motor failures, and compare SMERL to things like SAC, Diane, which is a diversity-driven skill learning approach, but isn't specifically used for optimizing task performance, as well as robust adversarial reinforcement learning, which kind of corresponds to one of the initial approaches that I was talking about, where you try to generate adversarial perturbations. And we measure 5-shot generalization. When comparing these algorithms, we find that with varying degrees of environment change, SMERL is able to be generally improve upon the robustness of the algorithms for varying obstacles, varying forces, and different degrees of motor failures. And intuitively, what these results are showing, if you look at a policy learned by SAC, you get something like this. And then if you get put an obstacle in front of it, it isn't able to reach the desired goal position. And then for SMERL, it learns a diverse range of policies that are controllable with a latent variable, some of which hop on the front foot, some of which hop on the back foot, and some of which do a front flip. And we see that when by learning these diverse solutions, there is one policy, at least one policy, that can successfully reach the kind of goal position on the right amidst this obstacle being present. Okay, I've talked a bit about robustness in simulation. What about the real world? We also considered a situation where we have one training environment. In this case, we want to learn how to grasp objects, and we want to be able to be robust to different test environments, such as drastically different lighting conditions, transparent objects that are particularly difficult, checkerboard backgrounds, as well as a substantial change to the morphology of the robot. And what we found is that in the original environment, using a state-of-the-art grasping reinforcement learning method, QT-opt, we're able to get 86% on the original environment, and performance drops substantially on the test environments. We're going to use a similar assumption to the previous approach, which is that we want to be able to adapt with a modest amount of data. And in this case, we're just going to use a really simple idea of just being able to trying to fine-tune the policy using a little bit of data on the test environment. We've seen that fine-tuning works well for computer vision, natural language processing, and other fields, but we haven't really seen it be demonstrated in real-world reinforcement learning contexts. So that's basically exactly what we do. We take a base data set of 608,000 grasps. We train a reinforcement learning algorithm, a base Q function using this data. This gets 86%. We then collect a modest amount of target data, in this case around 800 trials. Combine that with, initialize our target Q function and fine tune that using these 800 trials, and then take the adapted Q function and deploy it in the new environment. And what we find is that across a variety of different visual changes and physical changes, we see strong improvements even after 25 grasps. ImageNet pre-training performs very poorly, and overall the performance gains are substantial. Okay, for time, I'll skip the qualitative results. And also just briefly mention that that while we use an afternoon's worth, about 400 to 800 trajectories here, with meta-learning, we can also accelerate this adaptation process and adapt to distribution shift with only unlabeled data. Yeah, so to conclude, if you're interested in generalization, I think you should be thinking about broadening the training distribution and figuring out what assumptions that will allow your algorithm to generalize, which may be assumptions like predictability, local changes in the environment, and a modest amount of test data. And this allows us to learn amidst non-stationarity and extrapolate to new situations. With that, I'd like to thank my students. If you're interested in learning more about generalization, multitask learning, meta-learning, a lot of the lecture videos for my course are online. And if there's any time, I'd be happy to take questions. Thank you.
Thank you so much, Chelsea, for that great talk. And I'd like to introduce Emma Tegling, who is, she's been watching the chat message in YouTube, and we'll collect up 1 or 2 questions from the questions that have come up there.
Exactly. Thank you, Chelsea, for a great talk. We have one question that came up actually from Claire when you were discussing how you compensate for the non-stationarity in latent variables. If you could comment on the additional computation needed in LILAC versus SLAC, SAC, and PPO.
Yeah, that's a good question. So the computation at test time is, there's some additional computation with regard to predicting the latent variables as a function of the previous latent variables, but it's relatively modest in terms of the overall formulation. You essentially need to predict from the previous episode and then also roll out your policy. And all of this is done with feed-forward neural networks rather than with like iterative planning-based approaches. And so as a result, it's all quite computationally fast.
Okay. Another interesting question is whether you've seen any trade-offs between the complexity of the policy class and the adaptability. And maybe that also relates to the question how you actually know which ones are the best policies among the learned policies.
Yeah, so with regard to that second question, what we do is we simply just evaluate we run the 5, or in this case, we just run 5 policies. We sample 5 different latent variables, and we pick the one that has the highest return in the test environment. So we are assuming rewards for 5 episodes at test time, but not making any further assumptions. With regard to the first question, we didn't notice any that like they needed to necessarily change the architecture of the policy in order to make it more or less flexible. Although in general, larger policies will maybe a little bit more expressive. And of course, there's kind of different phenomenon in deep learning that show how a function class relates to generalization and training performance.
Okay. I actually had one further question related to the first part of your talk, when you discussed that it's actually lack of data sets that is an issue in reinforcement learning rather than the algorithms themselves. And do you think there should be a bigger push in getting benchmark data sets that are large and useful?
Yeah, absolutely. I think that we do need to be thinking about how we should be, what our data looks like and how we should be collecting data. I think that there's this really common practice in machine learning that's very healthy, which is to introduce new data sets all the time and use that to challenge the current algorithms. And I think that in reinforcement learning and control, we often collect our own data sets and operate with our own kind of narrow data from our own lab and so forth. And I think we should be thinking pretty critically about about how we might go about sharing data across institutions. This will not only lead to the ability to collect much broader data sets, but it will also lead to greater reproducibility and greater comparability of results.
Great. Maybe that's something that we can follow up on at the next L4DC workshop. Great. Thank you so much, Chelsea. I think that was all the questions that I had. Maybe Pablo or Claire want to fill in.
Oh, thank you very much. And thanks, Chelsea, for a fantastic talk. Wonderful way to end this year's conference. And thank you, Emma, for the moderation. Yeah, so we're at the end. And I think our organization committee would like to just come online and say a few concluding remarks. So we'd like to start by thanking several groups and several people. We'd like to thank our sponsors. This year we were very fortunate to have sponsorship from Bosch, Merle, MathWorks, and TRI. We thank them and we remind them that their sponsorship this year will roll over to next year in our hopefully in-person conference. And we'd like to thank ONR and NSF for their continued support, and AFOSR and ARO for their foundational support, in addition for the beginning of L4DC, which started last year. We'd like to thank all of our speakers, our contributors, our program committee, our reviewers, our moderators, and all who helped with L4DC, and to thank all of our participants. And it was just great to see the enthusiasm and the questions and the discussion coming up over YouTube. So thanks to everybody for your participation these past few days. We're also, as we did last year, and for those of you who are just joining for the first time this year, we're going to send out an email with a questionnaire as we continue to develop L4DC. As we said, this is only the second year of the conference. It's the first year that we've run it as a full conference with submitted papers, reviewed papers, and we have questions about the format. Obviously, this year is very special because of the online format, which presents additional challenges. But we'd like to get some of feedback about the conference as a whole. With that, I invite Ben and others to say a few remarks about as we conclude this year's conference.
Thanks, Claire. Actually, there's a question on the YouTube about where we will host this next year. Obviously, we really hope to hold this in person. The future remains more uncertain than ever, right? So, but hopefully if everything goes according to plan, we'll do this in person. We'll see everybody together. And we would very much like to hold it at Berkeley. We didn't get that opportunity this year. As you can see behind us, this is the view from my garage right there. I took that picture. Looks really nice. Yeah. Unfortunately, that's not true. Maybe next year it will be true that will be the view from my garage, but certainly I could take you to where we could get a beautiful picture like this when we get to meet next year in Berkeley.
Thanks, Ben. And are there any other comments from our organization committee? Pablo, Ali, yep. Melanie, George.
So let me just say something very quickly. Something that I think we emphasized last time. I think it's important that we emphasize again that this is your conference. I think pretty much. I think the whole committee. I think everybody is super open to to take it into whatever direction the community wants. So it's quite important that you guys step up, and make sure that that you have something to say in terms of either topics, format, whatever it is.
Absolutely.
Thanks, Pablo.
From my side, I just wanted to thank everybody for joining. I think it was great to see the community alive and the chat alive, and everybody happy to see each other. So definitely, we hope that we can do this in person soon. Thank you.
Ali, George, any closing remarks from you guys?
I just wanted to thank everyone for participating. It was phenomenal to see that we had more than 500 people yesterday. engaging with the conference. Just wanted to echo what Pablo said. I also wanted to thank MIT's foundational support for last year's effort, and we do hope that that you guys get to host it at Berkeley next year, so we meet in person.
Thanks, Ellie. George, would you like to give the final comment?
Well, I know many people worked, but I really want to highlight Claire and Ben for really leading the organizing committee. I think you know, they really stepped up at a very difficult time. So from the organizing committee, I would like to thank them for leading all of us. Everybody had a role, but I think they were leading us throughout this year. So I'd like to thank both of them for this year. Thank you.
Thank you, George. And thanks to everybody. And we hope that you enjoy the rest of your day, and we look forward to this conference as it continues to evolve. Thank you.
Thank you. Bye.